All right, introduction to sustainable energy. So, what are we going to discuss in this class? We're going to discuss the use of energy in advanced economies with an emphasis on fossil fuels, nuclear, and renewables. What are we not going to discuss in this class? Well, we're not going to discuss the use of wood and dung as energy sources, even though they are very important in um, underdeveloped countries. We're not going to talk about biofuels, except in passing, because these use as much energy as they provide. So biofuels like corn or sugarcane can be turned into ethanol, but in fact, the process of doing that requires as much energy as they provide. So I just don't think that that's a very important part. There is a chapter in your book about it. You can read that if you want, but you will not be tested on it. We're not going to talk much about climate change. Obviously, that is the elephant in the room, and um, and certainly sensitive to the issue of climate change, but that's not the focus of this course. We're not going to talk much about recycling, although recycling in many cases, especially for things like lithium ion batteries, would be very helpful in that. But and we're not going to talk much about saving the planet, which everybody is interested in. Geologists are less interested in saving the planet because we have the view that the planet is going to be just fine. It's going to be the people and the life on its crawling around its surface that may not survive. That is our perspective. Okay, so um, any questions about what we're not going to cover? All right. So why is a course in sustainable energy being taught by a geoscientist? Yes, Clint. Not
Well,
seeing?
I'm just kind of curious why we're not discussing recycling because that's tremendous input on the cost of some of the various, sources out
Like
there.
like what? Recycling what?
Windmill blades, solar
Oh,
panels, a
oh,
lot of this,
interesting. No, that now that would be an interesting course project.
so
But I and this we only have a semester to discuss this, but with the student projects, you can do just about anything. And it's all the other answer is it's not in the book. So I'm I'm a very happy professor when I find a textbook that I go, this gives me the structure of the course I want to develop. And that's what that book did. And it wasn't in there. So that's why it's not. But thank you for clarifying. Now, can you see this Q? Why is a course in sustainable energy being taught by a geoscientist? Is that it?
Nope.
The effort to move to sustainable energy should be a concern and interest of everybody in the world, and especially everyone in universities, including UTD. So that's one answer. So another answer is, while many UTD departments and schools do research on and teach some aspect of sustainable energy, none have the necessary expertise to teach all necessary aspects. We need to involve as many parts of the university as possible in this effort. And that part that I have not did not succeed in my career in doing that. Maybe I could have tried harder. Doesn't matter. Third answer is geoscientists have a big stake in energy via our traditional role in exploring for and helping to develop hydrocarbon, coal, nuclear, hydroelectric, geothermal, and natural resources. So even though we don't cover a lot of things like solar energy or um, wind energy. We don't see those as really geoscience related. We've got as much of a stake in energy as any of the other departments. So, and I really that another answer would be, look, nobody else is teaching it, so we might as well. So this is now that you see in the up there, the numbers correspond to the chapter headings in the book. So the energy crisis of the 1970s was a taste of what happens during an energy crisis. Also, what happened in February 2021 in Texas, which was when the ERCOT grid nearly collapsed, is another, sort of smaller scale example of an energy crisis. So energy, the more we depend on energy, the more vulnerable we are to energy crises. So good to keep in mind. Then there is the issue of sustainable development. So the book talks about the 1980s UN World Commission on Environment and Development. Sustainable development should meet the needs of the present without compromising the ability of future generations to meet their own needs. Okay. Sustainability principles in practice. Corporations usually focus on financial balance sheet, but more and more are also addressing social and environmental impacts. That's a tension that always exists. And it's interesting to sort of recognize this, and useful to recognize this, especially as we prepare our students to seek employment with companies. And then next section, challenges for sustainable engineering, is to institute sustainability considerations into projects and operations in much the same way that safety issues are now included. Safety is a big issue with companies, and even though they don't directly relate to the balance sheet, they do indirectly, and that's why they're being increasingly included. Companies don't like spending a lot of money, for disabled workers or dealing with lawsuits. So they're working hard to deal with safety considerations. And the lawsuits and liability for environmental concerns is in some cases reduced. For example, CO2 emissions, but in other cases, it's not reduced. For example, pollution in groundwater and things like that. So, but again, we've got this perceived conflict between economic benefit and sustainability that's always in the background of these discussions. And just raise your hand if you have a question. I'm happy to explore anything. Don't be shy. But we're in the middle of a transition in energy from fossil fuels to renewables. A big part of the challenge for the energy transition is rapid population growth. And this is especially true for Texas. So carrying capacity and exponential growth, two of the biggest challenges facing civilization in the 21st century are ensuring access to cheap and abundant energy in a rapidly growing population, and addressing the global climate change by transitioning to carbon-free energy sources. I mean, we take our access to energy for granted. So the average US household uses 877 kilowatt hours. And we're going to, one of the challenges of this course is getting used to the units that we're using. So kilowatt hours, that's 1,000 watts per hour of use, electricity per month. So that means the average residential daily consumption of electricity is 12 kilowatt hours per person. So each of us, in our residence uses that. So that's a lot of energy. For these reasons, energy challenges are the keys to humanity's future. If we imagine a dystopian future, we are energy limited. If we imagine a utopian future, energy is plentiful and cheap. So one key to meeting the energy challenges is to better understand where we get our energy. That is the motivation and the purpose of this class. So let's talk first about population growth. Now, the authors were professors, at least some of them were professors at Colorado State University, which is in Fort Collins, Colorado. And this is comparison of where Fort Collins, 1950, and Fort Collins 2020. So this is the map of Fort Collins in 1950, and it sits in about here. This is the present map of Fort Collins. So you can see this place has changed a lot. In 1950, the population was 15,000, and it was 3,700 acres of town surrounded by 50,000 acres of farmland. Farmland was being converted to residential at about 158 acres per year. So how long would this last? Well, you can go, okay, well, that's simple. 50,000 divided by 158 means 317 years. Well, you can see that's not what happened, because it's not the amount that is that's changing, it's the rate. So the rate of consumption of farmland is far more important than the amount. So the population growth rate, which in some way is going to be the consumption rate of the farmland, about 4.2%. And the conversion of farmland to residential land is correlated, right? But it's not farmland, it's residential land. All right, so here's out of your book. You can see it's pretty up to date. So here's Fort Collins, 1920. No, that we were talking about 1950, which would be about here. So farmland is slowly being converted to residential until all of a sudden it's all getting so, and the population's doing this. So today, population, yes,
Yes.
it's a plot of development, farmland versus population in Fort Collins, Colorado. Okay, so here we're looking at the world, the growth of the world's population. Global population in 2026 is about 8.3 billion. Yeah, is that about somewhere in there? Oh, it looks like we're ahead of schedule. So people still keep reproducing, and that is a really important challenge, because with population growth, everybody that comes along wants a good life, and we know what a good life is. It involves, housing, it involves access to education, it involves food. We know what it is. And people that are poor want to not be poor, and people that are wealthy want to remain wealthy. And energy use is a function of population, certainly, but even more importantly, it's a function of wealth, and the world is getting wealthier. So this population growth, we can't imagine a sustainable energy future without taking into account the fact that the people that want access to the sustainable energy there's more and more of us all the time. All right, so now do you see mathematics of exponential growth?
Yes.
Excellent. All right, so this is a very useful thing to know, because we're going to talk about exponential growth, but if you want to think about your own credit card debt, this is a very useful thing to remember. So suppose a quantity of N of something increases from the original quantity N naught at a continuous rate of R per unit time T. So the future quantity of that thing at any time is given by N of T is equal to N naught 1 plus R to the T. So it's a pretty simple equation. The T is the exponent, and this equation this is why we talk about exponential growth. Exponential growth is growth that can be described with an exponent in one term. So, okay, that's mathematically interesting if you're a mathematician, but more interesting perhaps to normal people is the doubling time. So that can be calculated by setting N is equal to 2N naught. And then you can rearrange this. The doubling time, D, is equal to the logarithm of 2, right? Because N naught is, N is now 2N naught divided by 1 plus R. And Thus, for a doubling time of 10 years, we put T, we solve for T. The only thing that works for that R, this component, this term R is 7%. So the rule of thumb is the doubling time is 0.7 divided by the R. So if you're investing money, if you can get a 7% return, you can double your investment in 10 years if you have a 7% return. Now, you can also look at the cumulative effects of inflation this way, or credit card debt, or anything. So, when you look at these credit card interest rates of 18%, if you run a balance, you're basically asking to go bankrupt. So, with credit cards, you've got to either pay off your balance every month or tear up your credit cards unless you like being under continuous financial stress. So life advice is hidden into this course occasionally. All right, so let's keep going because we're talking about population, the mathematics of exponential growth. Suppose that a finite resource, so for example, oil, has a total usable quantity of N sub T. If the initial consumption rate is N naught per year and does not change, then the resource timeline is, T sub L, lifetime, is N total divided N naught, right? The total amount of the resource divided by how much is being used each year. However, if the annual consumption increases with annual growth rate of R, then we can use that equation to calculate the lifetime in using this form. And this is a very useful way to think about non-renewable energy like fossil fuels. So a few years back, there was this discussion about, when we're going to run out of oil, and, but that implies that the consumption rate, the increase in consumption rate is zero, which is not the case. I mean, our demand for oil is increasing. And if the annual consumption rate increases with an annual growth rate of R, then the lifetime of the resource is expressed by that equation. And this is a useful way to think about non-renewable energy like fossil fuels, right? Now, people say, when are we going to run out of oil? And the answer is never. Now, I don't say that meaning that you're always going to be able to get gasoline at the pump at the same price. There will always be oil and gas available at some unspecified price, but we've seen remarkable evidence that the strength of the economy is tied most strongly to the price of energy. Right? If you think about how you get food to the grocery store, it's coming on trucks, and the price of that food could potentially be extremely high if it costs a lot of money for the truckers to fill up their diesel tanks. So we will run out of cheap oil and gas. When that will be is not known, but it will happen. And the best way to deal with that is to have other sources of energy that can take up some of that slack. So let's talk a little bit more about energy consumption in the United States versus the world. So we've talked about the growing population, and one of the challenges is if everybody's using the same amount or increasing the amount of energy, then that's going to be a real stressor on the national, the local, the global energy systems. This is an interesting diagram for a number of reasons. Left off, we were talking about energy consumption by year. And we've got two curves here. This is the total energy consumption, this darker purple line, which is kind of flattened out here, maybe going down a little bit. But what's most interesting is the energy consumption per person peaked around the 1970s and now is in a slow decline. That's a very helpful sign because we know that there's a lot more people in the world all the time, and if they all require increasing amounts of energy, we're going to have a more serious problem than if they start requiring fewer and fewer, right? So if we sort of look at where the United States is today, we got 4% of the world's population, 16%. We use 16% of the world's energy, and that is aligned with the amount of the world GDP that we contribute. So every day, the average U.S. person uses 2.5 gallons of oil, 6.6 pounds of coal. That gallons of oil seems a little low, but okay. And because mostly it's gasoline. But anyway, and 265 cubic feet of natural gas, probably more right now. In comparison, the EU has 6% of the world's population, 50% more than the United States, uses only 9% of its energy and accounts for almost the same amount of the GDP. China's got 18% of the population, uses 27% of its energy, and contributes 19% of its GDP. So there's an interesting heterogeneity in the way that different groups of nations and people use energy. Now, there is a very simple relationship between energy and what's called the Human Development Index here. This is the Human Development Index. This is from your book. And the HDI goes from 0.2 to 1.0, which is the maximum. Don't ask me what it's based on, but you can see that, Mozambique, Nigeria, Zimbabwe, these African countries, they're in a much less developed nature than, say, Finland, the United States, Iceland, Belgium, Singapore. Poor nations down here, rich nations up here. And you can see there's a relationship between energy use and national wealth, if you want to put it that way. And it's an interesting one. It's not linear. It seems that what happens is you need a certain amount of energy to reach a certain human development index. Italy, France, Belgium, Finland, they're all sort of on the same, they're all about the same in this HDI, but their per capita energy consumption is vastly different. Italy, use on the order of 3,000 kilograms oil equivalent per capita. So that's, as you will know, the units for energy are a source of frustration. And so I encourage you to be frustrated, but then don't worry about it. You're not going to be tested on all of the different types of wasting energy. Yes, Clinton.
And if you look at it and you see Iceland, you go, oh God, those oil hogs of the North Atlantic, except they're not using like hardly any oil, a little bit. They're using volcano juice.
Yeah, volcano juice. Yes, geothermal energy. Thank you. We'll be talking a bit about this. Yes, these countries that have these kinds of resources are sort of smug about it. But you're right. There's a lot more texture in this graph than we can cover with a single XY plot. But it does show you that energy use and national wealth are related to a point, and that's an important thing. So as we get richer, as nations move up this curve, they're going to be using more energy, which is a point we've already made in a different way. So Modern life requires access to energy, access to cheap energy. So on the order of 10 cents per kilowatt hour is key to economic development. Rich nations use 10 times the energy of poor nations per capita. And at the same time, we have to deal with the fact that we have decreasing hydrocarbon resources. And as we'll see in this course, hydrocarbons provide the bulk of energy for the world. So we're going to be facing that problem with hydrocarbons. We need to be facing that problem with hydrocarbons from the point of view of climate change, as well as dealing with economic reality. But making this transition to renewable energy is going to be problematic if it isn't done in a way that allows us to continue to rely on cheap, plentiful energy. So that is one of the huge challenges facing the world today. All right, now this is a sort of a similar plot. This is energy consumption per capita, kilograms of oil equivalent, versus GDP per capita in US dollars. This was back when the book was written, so it probably hasn't changed that much. But what we can see in general, there is kind of a linear relationship, right? But Norway and Saudi Arabia are using the same amounts of energy per capita as the United States, with a huge difference in the GDP per capita. So there's a lot of non-energy related things in here, but in general, there's a positive relationship, which isn't very surprising. So we want to move this way. We want to move down in energy consumption per capita without moving this way, without decreasing the GDP per capita, right? That is the challenge, the 21st century challenge. So, chicken and egg question. Does wealth follow energy use, or does energy use follow wealth? That's another way of framing the chicken and the egg question. Which came first, the chicken or the egg? And by the way, the answer is the egg, because there were eggs a long time before there were chickens, just in case anybody is wondering. All right, so rich people use a lot more energy than poor people. This is not a news blast, but if we look there on the left, we've got a rich guy. Okay, he's rich enough to get his head shaved every day, and he's taken his money and created something that I guarantee you uses a lot of energy. And on the right, there's maybe as many people living in that house as there is in the house on the left, but they are for sure using a lot less energy. So we can talk about energy justice, which refers to the goal of providing equal access to energy resources to all people. We're not going to say very much about that, but it is an important part of any fair economic system. And that is certainly a concern of many peoples, to strive towards fairness in our economic system, providing opportunities to all people. So here we got a map. This is showing the energy use per person in 2024. And you can see that this is going from 0 kilowatt hours to 100,000 kilowatt hours per year. And you can see the developed nations are all in the bright red, and Africa is not. South America is kind of in between. India is kind of in between as well. So this map shows the annual changes in primary energy consumption in 2024, and this is usually reflecting either a catastrophic event of some nature, or some massive improvement in energy. And you can see that Mongolia, Ethiopia, Zambia, and Laos, Cambodia have all gone through. What is that one? That is, I forget what that's not Turkmenistan. That's Turkmenistan. One of these central. What's that?
Tajikistan?
Maybe Tajikistan. Yeah,
I'm not sure.
These are all benefiting from some new energy projects. It's kind of interesting that Ukraine hasn't really seen that decrease because we hear about it quite a lot. But it's interesting that Eastern European nations are seeing or saw some decreases in energy consumption, probably because related to the shutting of the pipelines from Russia. So this is kind of an interesting map too. Now, China's energy needs are the gorilla or the elephant in the room. Now, we're going to make the point that China is a coal-powered economy, but at the same time, it is also a world leader in renewable energy. So we can see here that coal has been increasing in importance as an energy source for China all through basically for the last 40 years. But what's interesting is the fraction of renewables in here, hydropower, wind, solar, and bioenergy, they are increasing a lot. So wind and solar in particular. Now, nuclear is also increasing. Their oil consumption is, they're not using very much oil and gas to make electricity. In the United States, in contrast, we are using declining quantities of coal. We're using more and more natural gas. Now, this is not just electricity. This is a little bit of apples and oranges here because this graph is just electricity. This one is total energy. We don't generate electricity by burning oil. That's wasteful. That's most of that petroleum is being used for transportation. So we can see that the U.S. energy use, as we said before, is not growing much, but the mix of energy sources that we're using is, and in particular, coal is going down. So I just want to draw your attention to this new unit. We've talked about the quad before, but it's 10 to the 15 BTUs, which is British thermal units. So it's a lot of BTUs. And we talked about this. But this one is dividing it by sector. So this is everything except this is everything, and this is industrial only. And you can see the industrial consumption of energy is going down, and that's related to the deindustrialization of the United States. Okay. So if we compare here for how we generate all of our energy versus all of our electricity, we see that electricity is overwhelmingly created by natural gas in the United States. With uranium and nuclear and other renewable energy being second, and coal third, and hydropower fourth. Whereas if we look at our total energy generated, a lot of it is crude oil and condensate, and that's mostly goes into the transportation sector. So energy and electricity are related but different. And electricity is a subgroup of energy. So 5 key considerations for our energy future. We're going to need all the energy we can get. We will need all sources of energy, including fossil fuels. There is no way forward that is viable that's going to maintain the amount of energy we're going to need at the prices we require for a healthy economy unless we use everything. If you say renewables are nonsense, get rid of them, you're going to be in as bad of a place as if you say hydrocarbons are the problem, get rid of all of them. Those strategies may be politically satisfying to a purist, perhaps, but they are not a useful strategy for us. To address climate change, we need to decrease our emissions of carbon dioxide by increasing use of renewable energy and perhaps nuclear. Nuclear is the one option we have to have as much electricity as we want on demand, and we'll get to the importance of that in a bit. So renewable energy, and I should add, and nuclear here. Fossil fuels will make up the most important source of energy for the foreseeable future, but we want to decrease the use of high polluting and high CO2 generating sources like coal in favor of low polluting and low CO2 generating hydrocarbons like natural gas. And this is a point that many people who are opposed to fossil fuels miss, is some fossil fuels generate a lot of CO2 and other pollutants per kilowatt hour that they generate, and others generate much less for generating the same amount of energy. Obviously, we want to move from the more polluting, the more CO2 generating to the less CO2 and polluting generating. We need more and safer nuclear energy. Nuclear energy is a remarkable technology. It is very polarizing, and we'll talk a lot about the polarization. And there's no state that shows this more than Texas, because Texas has done two things that are sort of at opposed to each other. One is it's emphasized the importance of nuclear energy to Texas's energy future, and the other is it's passed laws outlawing the disposal, the storage of high-level nuclear waste anywhere in the state. So somebody else has to take the massive amounts of nuclear waste that we want to generate. So there's an inconsistency there that reflects the sort of schizophrenic attitude the public has about nuclear energy. And then finally, increasing battery storage is key for increasing the use of solar and wind energy. So we're going to talk more about that. Solar and wind energy is offered as a panacea, but it's not, because the wind doesn't always blow and the sun doesn't always shine. But if we can store the energy generated when the wind blows and when the sun shines in batteries, and we can use it later, then no problem. It's as good as a nuclear power plant or a natural gas generating power plant. So sustainable energy is not just renewable energy. It's not even mostly renewable energy, and it won't be for a long time. But sustainable energy means incorporating more renewable energy into the mix, which is going to be dominated by fossil fuels in particular, but hopefully also nuclear energy. Solar and wind energy are especially important. These generate electricity, and electric cars are also important. But I think you're getting the sense that this topic is complex. So one of the things we know is that as we move towards more renewable energy, this will increasingly load electricity, the grid, right? So Jaws, you're going to need a bigger boat. One of the best lines that came out of that movie, we're going to need a bigger electricity grid. And we had a little test of the ERCOT grid last weekend, and an ERCOT grid passed with flying colors. Well, there were a few outages, but nothing like it was in 2021, that's for sure. But electricity is going to be the future of energy more and more. So what are the goals of sustainable energy? Number one, provide cheap, abundant energy for all of civilization's activities at a reasonable price. This is the interest of economics, business, and engineering. Second, decrease CO2 emissions and other pollutants. This is the interest of science and policy. So here's some interesting comparisons for fossil fuel energy generation versus the CO2 output. Now, the units we're using here are megajoules per kilogram. No, it doesn't matter how much that is. The point is that to generate 1 unit of energy, per kilogram of CO2 generated, we have natural gas, which generates 18.3 megajoules per kilogram of CO2. Gasoline is 16.1, and coal generates less than half of the energy per kilogram of CO2. It's the dirtiest fossil fuel. And you can see why industry is moving towards natural gas. It's just easier to deal with. The economics are what favors that. There's reduce the reliance on imports. Iraq was in the news 20 years ago, and now Venezuela is, because the supposition is that the United States is causing these kinds of things because it wants to secure the energy that those nations had. It's causing other kinds of international political problems that crop up from time to time. So if a nation can reduce its reliance on import, it can decrease its potential for international friction. So that priority is the interest of international relations. And then finally, the goal, sustainable energy is going to require some new technologies, and this is going to create jobs and wealth. So this is the interest of engineers and entrepreneurs. And so those are very broadly speaking our goals. So let's move. Any questions about that? We're going to move into a new part of the introduction about energy basics. So just raise your hand and speak up, and we'll get to it. All right. What is energy and how do we measure it? All right. Yes, Clint.
Just real quick, one of the things that you'll notice is that there's a lot of units that we don't normally use in everyday speech, like kilograms of oil equivalent, quads, BTUs. I mean, why did the British get a hammerlock on the thermal unit? So anyway, is it all that tea they drank? Anyway, understanding the units is going to be very useful in understanding the material.
Well, I would modify that, understanding that you probably won't understand the units any better than I do, and not to obsess on that is what I would recommend, because these units are incredibly confusing. I tell people, there's 2 reasons that people are confused. One is they don't have enough background to understand what's being explained, and the other is the explainer does a very poor job of explaining material that the person does have enough background to understand. And generally speaking, when we're young, we tend to blame ourselves for not understanding stuff. But as we get older, we understand, there's some situations where if you're not confused, you're not paying attention. And I think energy units is in that group. It's not that something that a normal person would be able to understand. Just if you understand that you're confused and don't let that frustrate you and stop you from digging in deeper, that's the goal of my caveat to you about what we're about to get into. But let's talk about energy. What is energy? So there's a thermodynamic definition. Thermodynamics is the scientific subdiscipline of physics, chemistry, certain extent geology, that deals with temperature, heat, and work. Energy is the capacity to do work. There is an energy of motion, and there is an energy of potential for motion. So we distinguish between kinetic energy, which is the energy of motion, and potential energy, which is associated with potential for motion. And their little cartoon sort of shows you two examples of energy. Potential energy, the arrow's drawn back, the string is tense, and when she lets go, it's going to move, and that will be all of that potential energy will have been converted into kinetic energy. All right, so the first law of thermodynamics is that the change in the internal energy of a system, delta U, is equal to the heat of the system, Q, minus the work done by the system. So energy can be converted from heat to work and work to heat, but it cannot be created or destroyed. So for sustainable energy, we want to maximize W. And we can characterize that by the efficiency of a system, the W over Q. So here's some examples. There's a candle flame and a light bulb, and we can talk about which one is more efficient use of energy. So the candle flame, that is about 100 watts of energy, but it generates about 12 lumen of light for that 100 watts. And we're going to talk about what lumen are, but basically less lumen, it's not as bright, more lumen, it's brighter. So a light bulb is 60 watts, but it generates 700 lumen. So I don't think anybody would have trouble identifying the more efficient use of energy is a light bulb, not a candle flame, although, candle flames, they're quite romantic and mood setting, light bulbs less so. But I think you get the point. If anybody have any questions about the first law of thermodynamics and its importance for our discussions about efficiency, which is kind of a central point when it comes to designing energy systems. All right, now energy and power are sometimes used synonymously, but they're not. They are closely related, but they're not the same. Energy is the ability to cause change. Power is the rate that energy is used. So energy equals power times time. Okay? So when you see time in there, it is an expression of power because it's a rate. So the SI units of energy are the joule, capital J. That's 1 Newton accelerating a mass of 1 kilogram to 1 meter, 1 meter per second. So the SI unit of power is joules per second. And joules per second is the definition of the watt. So we've talked about kilowatts. Kilowatt hour is a unit of energy. 1 kilowatt per hour is 3.6 million joules. So here's Joule, dapper gentleman, who's responsible for our units of energy. And here's James Watt, the inventor of the steam engine, who's responsible for our units of power. Not that they named them, but that's who they're named after. All right, so what are SI units? This is the Système International des Units. This is obviously French. These are the modern form of the metric system and the world's most widely used system of measure. It's the only system of measurement with an official status in nearly every country in the world, employed in science, technology, industry, and everyday commerce. It it's complicated. There's 7 base units in the SI system there, which are the units of time, length, mass, electric current, temperature, numbers of atoms or molecules, and luminous intensity. So the second is the SI unit of time. The meter is the SI unit of length. The kilogram is the SI unit of mass. The ampere is the SI unit of electric current. The Kelvin is the SI unit for temperature. The mole is the SI unit for the number of atoms or molecules. And the candela is the SI unit for luminous intensity. And this system can support an unlimited number of additional quantities. And these are called the coherent derived units, which are directly related to the 7 SI base units. Sorry. So there's 22 coherent derived units have been provided. So the SI derived units, Newton, Hertz, Joule, Watt, Volt, Ohm, degrees centigrade, lumen, and becquerel are all SI derived units. Any question about that? It's a little confusing, but I think they did a pretty good job of explaining how it works. All right, SI units make life easier than non-SI units like horsepower and British thermal units, right? So we can convert non-SI units like horsepower and BTUs to SI units and derived units like the kilowatt hour. So 1 horsepower is equal to 750 watts or 0.75 kilowatts. BTUs, that's the amount of energy needed to heat 1 pound of water by 1 degree Fahrenheit. So that's hard to turn a pound, the pound and the Fahrenheit. Those are not SI units. But 1 BTU is about 3.4 watt hours. So the conversion is straightforward if you need to do it. You don't need to memorize these things. Just understand why SI units are so useful. All right. So as we said, energy is the ability to do work. Energy equals power times time. That, as we said, E equal P times T. And power is the rate at which work is done. So energy is what we pay for. So here we've got a number of appliances. We've got a mixer, pasteurizer, Cuisinart, whatever you call it. We've got, looks like a dryer. That looks like a washing machine. And that looks like a refrigerator. So the power that each of them needs is 200 watts to drive the blender, 1,200 watts to drive the dryer. The washing machines needs 2,500 watts, and the refrigerator needs 200 watts. But we use them for different amounts of time, don't we? Right? We're going to use our blender a lot less than we use our refrigerator. That's on all the time, we hope. And likewise with dryers and washers. So when we multiply this times this, we see what the energy is used. So this should be kilowatts. So that's 5 hours times 200 watts. That's 1 kilowatt, right? That's 1,000. That's 1,000 watts or 1 kilowatt. So 1,200 watts times 20 hours. That's 24 kilowatt hours. This one 75 kilowatt hours. This one 40 kilowatt hours. So together, these 4 appliances consumed, 140,000 watt hours or 140 kilowatt hours, right? And obviously, the more of those you have in your house, the more energy you're going to be using, assuming you use them all the time. Any questions about that? Let's talk about the energy in a gallon of gasoline. So 1 gallon of gasoline is 35 kilowatt hours of energy. So according to that, we can calculate a $3.50 gallon of gas will cost about 10 cents a kilowatt hour. So that compares very nicely to electricity. So electricity is, you're paying somewhere between 11 and 16 cents per kilowatt hour. So in a sense, gasoline is as cheap, if not cheaper, than electricity. We don't normally think about gasoline like that. We normally worry about miles per gallon. But yes, Clint.
One of the things you get out of this class is a way of thinking about stuff you already knew about in different ways. For example, comparing battery power with a stick of wood or a piece of coal, which has been described by Isaac Arthur as a battery that can hold its charge for 300 million years, but you can't recharge it. But that's a different, and it pollutes, but that's a thinking about energy in different ways, and that helps us to approach solutions.
Indeed. All right. So how do we measure energy? A lot of ways. It's confusing. Unfortunately, there's lots of online conversion tools. So we, these are units of energy. So let's start up here with the electron volt. This is often used by physicists working with particle accelerators. And 1 joule equals more than 10,000 quadrillion electron volts. And we got joule, that's the SI unit that, every second, each person transfers about 100 joules of thermal energy to the air around them. So that's kind of an interesting factoid. Then we've got the therm, which is the unit of heat energy equivalent to 100,000 BTUs, which is the amount of thermal energy contained in 100 balloons filled with natural gas. I'm guessing those are normal size balloons. The kilowatt hour, that's commonly used to measure the amount of electricity used by consumers. You guys should be familiar with that, those of you that get electricity bills. The BTU, often used to measure natural gas usage by consumers. 1 BTU is roughly equivalent to the thermal energy given off by an ordinary match. So that kind of a useful, now you understand. And we've got the 2 calories, right? We've got the food calorie and the gram calorie. So the calorie is, what we worry about, those of us that are getting fat, myself included, is commonly used to measure the energy available in food. So it's, 1 food calorie is equal to 1,000 gram calories. And a gram calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. All right, so let's start off. Yes, Caleb.
I'm just curious, what is a becquerel? I've never heard that.
A becquerel is a measurement of nuclear energy, and we'll be seeing that later. Becquerel was a French scientist, and when hold that question until we get into nuclear energy. But thank you.
Okay.
Okay, so let's think about how we measure power and energy. We didn't start doing that until James Watt invented the steam engine, and he wanted, you invent things often because you want to sell them. And at this time, back in the 1700s in England, the challenge was emptying coal mines of water, and it was being done by horses. And Watt said, why don't you buy my steam engine and it will do the work of so many horses? And the question would be, well, how many horses will it do? And it's like, okay, let's figure it out. So what he did is he came up with a measurement called a horsepower. And so this is 1 horsepower is the ability to lift 550 pounds, 1 foot in the air with a simple pulley system in 1 second. And okay, you might say that's funny. Well, but I mean, at the time, that's what was needed, was some way to compare how many horses one of Watt's steam engines would replace. So here we've got we love horsepower because that's how we talk about our cars, right? And stuff like that. So here we've got a small car, which has got 100 to 150 horsepower, mid-size, 200 horsepower, large, 300 horsepower, semi-truck, 400 to 600 horsepower, locomotive, 2,000 to 4,500 horsepower, an aircraft carrier, 260,000 horsepower. And the most powerful thing we can imagine that we can measure with horsepower is the Saturn V booster, 160 million horsepower. So you guys probably take a look and figure out what horsepower you have in your car, and then you can, well, if you have one of these with, performance cars, you can brag, but maybe if you have a Honda Civic, maybe not so much. Yes, Clint.
Remind these people that a Saturn V was not an automobile built by the Saturn.
Yes,
car
it was the
company.
rocket ship that took the astronauts to the moon. And yeah, thank you. All right, this is in your table. This is in your book. So this is table 1.6. The first midterm will be you'll be required to spit back all of these. Not. No, I'm not. I'm evil, but I'm not that evil. Let's put it that way. So here we've got, some BTUs, quads, calories, kilowatt hours, megawatt years. I mean, it's crazy. It's in your book. If you get confused, just look at it. But I really like knowing how much energy is relative to something tangible. Geologists like things tangible, you know. So the SI derived units here are the kilowatt hour. That's 100,000 watts per 1 hour, and the megawatt year, which is 100,000, a million watts for 1 year. So, these are focused on the SI units, and most of these are not SI units. These two are, these three aren't. All right, so let's talk about joules. So Joule was a physicist, English physicist. These guys are all pretty much English, it seems. Well, that's not true. And we've already talked about what the joule is. The joule is also useful for electricity because it's also the energy dissipated as heat when an electric current of 1 ampere passes through a resistance of 1 ohm. Then with watts, we've got the unit of power. So when an object's velocity is held constant at 1 meter per second against a constant opposing force of 1 Newton, the rate at which work is done is 1 watt. That's a little confusing. You don't have to memorize it. But a watt is basically 1 joule per second. So let's think about our own experience. A 100 kilogram person, so that'd be 220-pound person, climbs a 3-meter high ladder in 5 seconds. We've all done that. And they're doing work at a rate of about 600 watts. So, a laborer over the course of an 8-hour day can sustain an average output of about 75 watts. Higher power levels can be achieved, obviously, for short intervals and by athletes. It'd be fun to calculate the watts expended on the Seattle Rams game yesterday. That'd be fun. Well, it would be fun for somebody, not me. And 1 horsepower is equal to 745 watts. So power. Now, there's also units these are also useful for electricity, and gets confusing, but these are the gentlemen that played important roles: Ampere, Andre Marie Ampere, Count Alessandro Volta, and George Ohm. And so So 1 watt is equal to 1 volt times 1 amp from Ohm's law, right? And also 1 watt is equal to 1 volt squared divided by the ohms of resistance. And this is a very simplified, electric circuit, right? There's a source of the electricity, and the current flows like this through a circuit, meets some resistance, and that's the relationship between resistance, current, and voltage. Voltage is equal to current times resistance. Power is equal to current times voltage, or current squared times resistance. You don't have to memorize those things, but they're related. So energy, we can use prefixes, which will allow us to use the SI units for much bigger quantities. So the prefixes of interest are the kilo, the mega, the giga, the tera, and the exa. So a kilo is 1,000. That's abbreviated K. So 1 kilowatt is equal to 1,000 watts. Mega is 1,000,000, abbreviated with a capital M. 1 megawatt is equal to 10 to the 6 watts. Giga, that's a billion, abbreviated G, capital G. 1 gigawatt is 10 to the 9 watts. Tera, that's a trillion, and that's abbreviated with a capital T. 1 terawatt is 10 to the 12 watts. And exa is, what is that? Trillion, quadrillion. That's 1 exajoule is 10 to the 18 joules. So just to keep in mind, a typical candle flame is 80 to 100 watts. And what we can see here is the power demand from 0 to 100,000 megawatts, right? 100,000 would be, that's 100,000 million. That would be 100,000 million would be a lot. Okay. If you were a light bulb, what would be your power? All right, so here we've got a 60-watt incandescent light bulb, sort of standard light bulbs. We've all replaced them. It puts out 840 lumens. So as we said before, the candle frame uses more watts to put out far less lumens, right? And this is a matter of efficiency. So the lumen, which we haven't talked about, is a unit of luminous flux. It is a SI-derived unit. It's not an SI unit. It's basically a measure of the perceived power of visible light emitted by a source, right? Something with more lumens is going to be brighter than something with lower. And there is this relationship between watts and lumens. What we want are lumens. And we want as many lumens as we can get at as low of a price as we can get, right? Because we have to pay for the watts regardless of whether or not we get the light we want or not for that amount of energy. So here is a synopsis of what kinds of ways we can get light. And it's almost a political argument. People don't want mandated high efficiency illumination sources because it's the government telling them what to do. But there's a good reason for trying to motivate people to get more efficient things. So here we've got the brightness in lumens, 220 plus, 400, 700, 900, 1300, right? Low light to high light from 4 different light sources: a standard, a halogen, a compact fluorescent light bulb, and a light emitting diode, LED. So we can get 220 lumens for 20 if we put in 25 watts into a standard bulb, or 18 watts into a halogen, or 6 watts into a compact fluorescent, or only 4 watts into an LED. So that's a huge difference in the energy required, and thus, this is a much more efficient way to generate light than this. And this is more efficient than burning candles. Okay, so using LEDs and CFLs instead of the standard incandescent bulbs requires less power and is easy money-saving energy reduction. Maybe you don't get anything else from this class, then you understand why it's in your economic best interest to invest in these CFLs and LEDs in your living area. All right, now I have trouble keeping units straight. So I like to relate things to Comanche Peak Nuclear Power Plant. So it's not far from Dallas. It's in Glen Rose, 60 miles to the southwest. It's got 2 reactor units, 1,300 employees. I'm sure there's plenty of job opportunities there. Unit 1 generates 1,218 megawatts. Unit 2 generates 1,207 megawatts. So in 2017, the annual output was over 17,000 gigawatt hours. 27th most productive U.S. power plant. So 17,000 gigawatt hours is 17 terawatt hours. So you may recall that China right now, or recently, was using 7,000 terawatt hours for the nation. So if we wanted to power China with Comanche Peak type nuclear power plants, we would need 411 of them. Now, another way we can play with these numbers is how many 60-watt light bulbs can Comanche Peak light at a time? So we've got 2,425,000 watts. Each, how many of 60-watt bulbs? About 4 million. So you could be 4 million light bulbs turned on at one time, taking that. All right. So each of us gets an electricity bill. Before I started teaching this course, I just paid it. And now I actually enjoy looking at it because I want to understand it a little bit more. This was a while ago. And so here's the billing period, right? That's 1 month. That's the previous month. And this is the year before. So the billing days, the electricity used in kilowatt hours, and the average daily use. So at that time, I was paying, 10 cents a kilowatt hour. Not bad. So here we're seeing the peak hourly electricity demand in each day. Okay, so each day there's a peak in electricity use. It's usually late afternoon, depends on the time of the year, as you can see very strongly. Here we're looking at, thousands of megawatt hours or gigawatt hours. And we're going from January through the year. And you can see that the electricity demand peak goes from about 50 or 60 in the wintertime to 80. That was back then. That was, it's higher now for sure. So we've got to be able to cover this. It's nice that it's lower during most of the year, but August, September, when those air conditioners are really on full blast, you've still got to cover this or else the grid goes down. So just looking at that, how many Comanche Peak equivalents does Texas need? So 85 gigawatts, which is low now, divided by 2.4 gigawatts for Comanche Peak, it would need 35 of them. Now, mind you, there's only 2 substantial nuclear power plants in Texas. One of them is Comanche Peak, and the other one's down by Houston. But that gives you sort of an idea of the situation. And we're going to see that the demand for electricity power is increasing much faster today than it ever has. So this is sort of telling us how the Texas electricity grid generates electricity, you know, nuclear, coal and lignite, natural gas, by far the most electricity is generated. A little bit of power storage, that's increasing rapidly. Hydro, almost nothing. Wind, quite a bit, and solar, you know, quite a bit. So we've, you know, just for the ERCOT grid, we need all of these sources of electricity. Now, the interesting thing is in June of 2024, the Public Utility Commission of Texas said that ERCOT expects power demand to nearly double by 2030. Now, that is an eyebrow-raising statement. But basically that the ERCOT grid needs to be prepared for demand that's no longer 85 gigawatts at peak, right? This is 85 gigawatts at peak, to 150 gigawatts at peak. And the Public Utility Commission expects, you know, some of this to come from growth in the state population, but, you know, 60% is going to come from Bitcoin mining and data centers, including those needed for artificial intelligence. So there's a huge growth ahead in Texas electrical energy. And I don't think I have to state it too strongly that that creates job opportunities for people like you. Okay, so this is January 14th. I think we've already sort of looked at that from the ERCOT website. You know, this was what I saw there. The demand is well below the supply. There's no problem on the grid. And then what's happening with the renewables, with, you know, the solar coming up with the sunrise and going down with the sunset, and the wind energy changing. So we don't have to spend any more time on that. All right. So keeping in mind this Comanche Peak nuclear power plant energy, and we said it was number 27 in US power plants at 17 terawatt hours. What's the biggest one? And the answer is the Grand Coulee hydroelectric power plant on the Columbia River. There's 4 power plants, could generate a total of 6,809 megawatts, which is a lot more than 2,400. But the annual generation of 20.2 terawatt hours isn't that much more than what Comanche Peak generates. And the answer is the river goes up and down. The power plants respond to the amount of water flowing through the turbines. So it's quite variable how much power it actually produces. Whereas a nuclear power plant, you really can't turn it off. Once you turn it on, it's going to be generating that much power until you turn it off. So we want to make a difference between the capacity to generate and what is generated. And this becomes very important when talking about solar and renewable energy, because they have high capacities, but they're not using it all the time. You know, in the case of the sun and the solar power, that capacity to generate electricity, it applies when the sun is up. There's, you know, even though it's got a capacity to generate tremendous solar energy, if the sun's not up, it's not going to generate anything. Same thing with the wind. So keeping this difference in mind between the capacity to generate electricity and what's actually generated, as demonstrated by the difference between a nuclear power plant and hydroelectric power plant is a very useful thing to do. So let's move on to quads and exajoules. A quad is a unit of energy equal to 10 to the 15th, a quadrillion BTUs, or 1 times 10 to the 18th joules in SI units. So a quad is basically an exajoule, and it's equal to 28,000 gigawatt hours, which is 1.5 times the annual production of Comanche Peak. So quads is a unit used by the U.S. Department of Energy in discussing world and national energy budgets. So the global primary energy production in 2023 was 638 quads or exajoules, your choice. Okay, that's confusing, but nevertheless, you get the idea that a quad is a bunch of energy, as is an exajoule. So where do we get, so that sort of finishes the discussion of units, which is good. We got through that because now we can move on to where do we get energy and what do we use it for? So we use about 100 quads of energy per year, and there's 9 main sources, 3 fossil fuels, which comprise about 80% of the energy that this nation uses, and then the 6 other sources contribute about 20%. So that's where the energy comes from, and what is it used for? So there's 4 main uses: industrial, transportation, residential, and commercial. So you can see that industrial and transportation use the lion's share of the energy, but we need enough to live and to go to stores, and businesses need it to run their places, right? Now, this is how the textbook shows sort of the flow of energy in the US between the sources of energy on the left and the sectors of energy use on the right. So this is, coal, natural gas, crude oil, not sure what that is, nuclear energy power, renewable energy. This is from the book for 2016, petroleum imports, other imports, and then, processing in here, where we get the energy from, and then what we've talked about, how the energy is used. That's how the book shows it. This is how the Lawrence Livermore shows it. These are all of the energy sources on the left: solar, nuclear, hydro, wind, geothermal, natural gas, coal, biomass, and petroleum. And these are how we're using it: residential, commercial, industrial, and transportation. But the nice thing about this diagram is it not only distinguishes, electricity generation and how it uses energy, but it also talks about rejected energy that's put into the environment, basically waste energy. Okay. So these are the 4 sectors of energy use. We'll talk about them a little bit more: industrial, transportation, residential, commercial. Industrial, those are facilities, equipment used for producing and processing goods. Major uses: chemical production, petroleum refining, metal smelting and refining. Those are the main uses. Transportation, we know this pretty well. Vehicles transport people and goods on ground, air, and water. Gasoline, diesel, and aviation fuel. That's the main thing that goes in there. Residential, living quarters for people. Space heating, water heating, lighting, air conditioning, refrigeration, electronics, and, wet clean, dishwashers and clothes stuff. And then commercial, service providing facilities and equipment, businesses, governments, and other institutions, focusing on lighting, heating, cooling, refrigeration, water heating, ventilation, and electronics. So that sort of, summarizes how we use the energy. So maybe we have time to get through a little comparison of Texas and California electricity generation. These two states are kind of the bad boys of the United States. They're very different setups of the government and sort of perspectives of different things. Texas is dominantly Republican, California is dominantly Democratic, but they all need electricity. So let's start there, and then we'll move on to some rapid change in Texas electricity generation, which is wind and solar replacing coal. All right, so let's just a few basics about how do you generate electricity. You generate electricity by spinning a magnet inside a coil of copper wire. So basically, you know, everybody's seen this. This is coil of copper wire. These are magnets. You spin that, and that generates electricity. So that's it. Simply, this is what it looks like. You know, a Siemens megawatt, 500 megawatt Siemens turbine, right, driving a generator set in yellow. So that's how you do it in real. But there is one way to generate electricity that does not require this, and we will talk about that in this class. Energy sources in Texas to generate electricity by ERCOT. Okay, so nice pie diagram. And here we can see wind. This is 2024, so it's not too far out of date. Nuclear is about 8%. Gas is 9%. And you're going, wait a minute. Gas is 9%, but gas CC is 35%. What's going on there? We'll get into that. Solar is 10%, and that's growing. Coal is 13%, and that's declining. The wind is 24%. So that's the energy sources in the state of Texas at present. Basically, it's dominated by fossil fuels. It's about 57% fossil fuels, mostly natural gas. And we're going to talk about some of the tensions that happen as renewables become a bigger part of the grid. And one of my favorite stories in this class is what we call the duck curve, and that quacks me up. So we'll get into that. All right, so here we've got Texas on the left and California on the right. And okay, this is confusing because the sources are different and they haven't been made similar, but let's just go through here. So let's start off with the least popular fuel type, coal, 13% in Texas. Okay, there's, you know, the coal generated electricity in California is almost zero. And that makes sense. California has no coal resources. It's expensive to bring coal to California, so why bother? Now, wind in Texas is 24%. In California, it's about 6%. So Texas is much more invested in wind energy than California is, and California that's not an insignificant part of the energy budget. And then gas CC and gas just regular is a total of 46%. And here, what we can see in California, gas is 34%. So they sort of combine gas, the CC and the regular gas into a single category, 33. So Texas is using a lot more gas proportionately than California. Oil, less than 1%. You know, that nobody in their right mind burns oil to make electricity unless you're in Saudi Arabia or some place that has too much oil. Now, nuclear, 8%. Nuclear in California is about 7%. Both of them are important, and there's some interesting developments in nuclear energy that we'll get into in a bit. Solar in California is almost 19%. In Texas, it's 10%. So California, according to this one, this is 2024, is ahead of Texas in percent of electricity generated. Although recently I've seen that Texas is ahead of California in solar generated electricity. We'll just have to sort of say they're both heavily invested in it. Now, the one thing that California has that Texas doesn't have, actually, there's two things. One of them is hydropower. There's a lot more relief in California and bigger rivers flowing over that relief that can be dammed up and you can generate electricity that way. So that's almost 12%, very significant. And the other thing that California has that Texas doesn't have is geothermal. That's a much smaller part of the budget, but of California's energy budget, but it's definitely there. So the point is that these two states have some similarities and differences in where they get their energy for electricity. Okay. And, don't hesitate to ask questions because it is interesting. Both of them are been stressed with their grids in different ways in the past. And both of them are going to be experiencing tremendous growth in electricity demand in the future. Okay, so what we can see here is the growth in solar energy in Texas. This is really quite remarkable. I haven't been able to get an update, but just for comparison here, this is capacity, not generation, right? If you put a solar panel out, it has the capacity to generate this much energy, but the sun doesn't shine 24/7. So the capacity is quite different than what is actually produced. But nevertheless, the capacity of solar energy in Texas now is these are installations. So it's probably on the order of 12,000 megawatts or 12 gigawatts, where that's be on the order of 5 times the Comanche Peak already. Now, the other interesting thing in here is it's divided by residential. That means, rooftop solar panels. Commercial, that means building top solar panels. Community solar, where communities get together and invest solar energy. And then utilities that put these things in. And you can see that the solar energy profile of Texas is dominated by the utilities. They're investing heavily in it. And for some reason, residential solar hasn't taken off. And that's a curiosity about Texas as opposed to California. All right. Yes, Caleb.
I'm just curious. So if those solar farms, would they be categorized under utilities?
Yes. Yes. That's investors come in, set them up. There's a lot of work to hook them up to the grid, a lot of permitting, things like that. But yeah, these are companies. All right, so what you can see here in the utility scale solar capacity, which we just talked about, the top 5 states are California, Texas, North Carolina, Florida, and Arizona. Makes sense, right? You might wonder, oh, well, maybe, Florida should be in there, but, rather than North Carolina. Oh, there it is. But it's lower than North Carolina. And in Arizona, you'd think would be much higher. Gosh, the sun that it has is amazing. But you can see how fast Texas solar energy is rising and on a path to surpass the utility scale solar capacity in the not too distant future, if it hasn't already. So you can see that's 2022. By the way, this is from the Energy Information Administration. I get a lot of information from them, and you might want to just look at them from, see what they've got. They have lots of different things about energy. So wind energy in Texas continues to grow very rapidly. So in 2023, wind power accounted for 28, almost 29% of the state's Energy generation, I think that would probably be electricity generation, second only to natural gas. We've got 239 wind energy projects, more than 15,000 wind turbines. It's, by far the most wind powered state in the United States. And there's a long history of wind power in Texas for good reasons, because there's a lot of wind in Texas and cheap land to put wind turbines on. So more than we have 40.5 gigawatts of installed capacity, more than a quarter of all the wind sourced electricity in the US. And wind power passed states nuclear generation electricity for the first time in 2014 and coal fire in 2020. So it's a remarkable growth. So here you can see the wind energy generation. There's a bunch of things in here that we're not going to talk much about. But wind is this pale pink. And the other thing that's rising is this slightly darker pink, which is the solar. And you can see when the grid needs the most help, right? This is sort of the peak hourly load for Texas electricity, the peak demand through the year. This is only, this is going through basically, like, maybe I cut it off a little bit, but you can see that summertime is when the peak is, in July, August, September. That's when we need the most additional electricity. So you can see the importance of solar energy in Texas. And you could argue, solar energy in Alaska wouldn't really help because their peak demand for electricity is going to be in the wintertime when they don't have solar. But in Texas, the peak demand is exactly when we have the most sunshine. So it's crazy not to move in that direction. All right. Now with wind, we look by the nation and we can see that the wind blows at different times of the year. So here we can see this is the Northwest, California, the Upper Plains, the Lower Plains. The rest of the United States is all of this gray stuff, and then New England. And what you can see in the Lower Plains is the peak of wind is in the spring, and actually wind falls off in the summertime. So you've got less wind energy than you do in the summertime than you have in the spring. So in California, it's quite different. The wind is at a peak in the summertime and then declines. So, these kinds of things have to be paid attention to as you're planning a project or trying to think about, what's going to be the rate of return on my investment. Well, wind energy you have to think really hard about these kinds of issues. All right. So then we're going to talk about the grid in this class. We'll talk about how electricity is delivered to customers, right? So that's where we are. There's the power plant, and then, basically taking the high voltage transmission lines. We'll talk about why they need to be high voltage, and then do a power substation, which reduces the voltage that we can use, right? So we'll talk about the grid and how the grid is organized. This is a really important part. And we have a number of grids, and this has been slightly politicized in the past. It was politicized after the 2021 ERCOT breakdown. We don't hear much about it anymore, but it's always in the background. This is how it's grown up. Yes, Clint.
And just real quick, one of the things I learned in this class and elsewhere is that we can blame the Nazis for ERCOT being just here, because there were a lot of individual little grids, and we had to link them up really quickly to build ships on the Gulf to export oil to the Allies in World War II. And so we just like, okay, stick it all together, plug it in. And this is ERCOT being separate is a legacy from that. So damn it, Hitler.
Yeah, well, we can decide whether this grid setup is good or bad. It's certainly worth discussing, but the reality is that wherever the grid is, everything has to be, the electricity has to be finely tuned. And a lot of what happened in 2021 has to do with what happens to the grid when demand exceeds supply. And we'll talk about that. So this is the ERCOT grid, which is, ERCOT is not a company. It's a nonprofit, and it is designed, an independent organization designed to take all of the energy providers, those are companies, and the energy that is transmitted over the transmission lines, which are also run by companies, and coordinating it. So this is where it gets a little confusing, because these grids are actually made up of what are called various independent service operators, or ISOs. So you don't see the word ISO in here, but ISOs are in these grids. So here are the ISOs. There are 10 ISOs, or RTOs, regional transmission organizations, and that they serve 2/3 of the electricity consumers in the United States and more than 50% in Canada. So the ERCOT ISO corresponds very nicely to the ERCOT grid. Now, the Western Interconnect here, which is most of the Western United States, that is, here is the California ISO as a sort of a part of that. So I'm always confused about the difference between the separate, the 9 separated grids and the ISOs. And I probably don't explain this very well because I don't understand it very well, but your book talks about it. And I think it's useful to be aware of these kinds of organizational structures, but you won't be tested on it. All right. Now, one of the questions is, how many electricity companies are there in Texas? And you'll go, that's an interesting question. And the answer is a bunch. There in Texas, there's 4 companies that deliver electricity to most of the state, not all of the state, but most of them: Vistra, Encore, NRG, and CenterPoint. And the way it works is, there in 2002, there was a deregulation of the Texas energy market, and Texans, you get to choose your own electricity provider. So there's 70 companies that provide electricity, even though there's 4 of them that mainly deliver electricity. So you have various source choices in your plan, such as renewable energy consumption options, which is an interesting thing, right? These companies offer 100% solar and wind power. Now, how do they do that, since the same thing is coming out of everybody's plug? But they generate their electricity entirely using renewables, as they say, and then they put it into the grid, and then you pay them for their part, but you're getting the same electricity that everybody else is. So there's different types of energy that, there's different kinds of contracts, even plans that offer annual summer energy rate freezes. So it's confusing to the average person, when they're asked. Most people just look at the bottom line and go, what's the cheapest, right? That's what I do. So think about it. If you buy electricity from a renewable only company, how do you get it? So you'll get these kinds of ads, 100% renewable energy plans. And okay, that's who you're paying, but you're still getting the same electricity. Okay, so here's how the system works. So we generate, we transmit, and then we sell. So there's three different kinds of electricity companies in Texas, and they work together. So we're generally interacting with a retail electricity provider, except occasionally a professor will ask one of these companies if they'll give them a talk. Sometimes they'll respond, sometimes they won't. But you're paying the bill to the retail electricity provider, and there's 28 of those, right? You get to choose between 28 of them. Then there are 5 companies that are involved in transmitting and distributing electricity from the sources of generation to the uses of electricity. So we don't interact with those. These TDSPs are, they're critical because they maintain the meters, the wires, the poles, underground cables. They're also responsible for reading your meter and providing that information to your retail electricity provider, these guys. And then these are the generators. Now, this is a very interesting part, and we'll be spending most of our time talking about this. And there's 1,490 generating plants in Texas. 2 of them are nuclear, 14 are coal, 101 are gas. There's 77 wind farms with more than generating or with a capacity of greater than 100 megawatts. I'm not sure which. And then 25 solar farms. So that's a lot. Now, going back to seeing that how the grid is going to be experiencing really rapid demand and growth in the next few years, this number is going to change a lot. And one can imagine that this mix is going to change a lot as well, right? So ERCOT, we'll talk a little bit about ERCOT. And it is basically managing the flow of electrical power to 26 million Texans. So ERCOT is not one of these 3. It's managing the grid. So it's also the ISO for the region, and it schedules power on a grid that connects more than 54,000 miles of transmission lines and 1,250 generation units. It provides financial settlement for competitive wholesale bulk power market and administers retail switching for 8 million premises. Anyway, it's a nonprofit corporation. It's got a board of governors subject to oversight by the Public Utility Commission of Texas and the legislature. So we've got 5 videos here. They should be short. Let's watch them.
In North America, there are 3 electric grids: the Western Interconnection, the Eastern Interconnection, and the ERCOT Interconnection. For historical reasons, the ERCOT region has been able to operate as its own interconnection. ERCOT's policy direction comes primarily from the Texas Public Utility Commission, guided by the Texas legislature. That's given the grid operator the ability to manage a wholesale electricity market that operates differently from most other parts of the country. It's proven very effective, giving most consumers competitive rates while also encouraging innovation and fostering different kinds of generation. In turn, this helps people come to Texas and create new entrepreneurial business models to serve the electric market. ERCOT, your power, our promise. ERCOT provides a central place where generation is dispatched out onto the grid and where generation and load are balanced at all times. ERCOT is similar to an air traffic controller. It doesn't own the airplanes or the runways, but it steps back and makes sure everything is flowing properly and efficiently. ERCOT doesn't own the assets. It doesn't make electricity, but it monitors all the moving parts that keep electricity flowing and keeps the markets that provide electricity to Texans running. There are a number of participants in ERCOT's market that make electricity work in Texas, starting from your home. Your home receives electricity from a distribution company. The distribution company receives electricity from the transmission system, which is what ERCOT is managing in its control room. ERCOT has prepared for the future in two primary ways. One, to make sure its people, systems, and market participants have the right rules to manage a changing system. Two, from a technological perspective, the grid operator has to be very sophisticated in order to manage the future of the electric grid. The best thing about ERCOT is the people, committed to the mission of making sure electric power will always get to the people of Texas. ERCOT, your power, our promise.
For more than 75 years, the Electric Reliability Council of Texas, or ERCOT, has provided the people of Texas with dependable, reliable electric services. With 24 million consumers, over 46,000 miles of transmission lines, and more than 600 generation units, there are many moving parts to power the region. To keep Texas running efficiently 24/7, ERCOT has implemented a state-of-the-art control room that gives grid operators the ability to successfully manage 90% of the state's electrical grid.
We balance the generation on the system with the consumer's demand at every point in time. So on each shift, 24/7, we have 9 folks in the control room to monitor the transmission grid, to monitor the generation that's being put into that grid, and to monitor forecasted demand and make sure that the grid stays reliable based on all of those factors. There is a lot of information that flows into this control room. What we have changed over the last 5 years is designing new tools, new monitoring displays that get that information to the operators in a way that's actionable, that they can use it, that they know what they need to do. It has lots of alarming features, green, yellow, orange, red type displays that will ratchet up as things become more pressing so that the operators can do their jobs better. We've put more focus on forecasting both wind and solar resources. We've added a second wind forecast, and then we've added 2 solar forecasts to be prepared for the growth of solar that is expected. The new Reliability Risk Desk, its primary focus is to look at things that are a little outside the ordinary. We normally operate the system for expected conditions and for unexpected things that could happen. But the Reliability Risk Desk goes beyond that, looking for things that are even more unexpected and try to maintain the reliability of the system even in those conditions. The promise of ERCOT is to be able to use the resources that are provided by the market to serve consumer demand in an efficient and reliable way. The control room is really central to providing that reliable and efficient generation to loads for the 24 million Texans that are hooked up to the power system of ERCOT.
With a state-of-the-art facility, the latest forecasting and risk assessment tools, and an innovative workforce, ERCOT is committed to providing Texas with a system that is reliable today and tomorrow and for years to come. ERCOT, your power, our promise.
ERCOT relies on all generation resources to help meet demand on the electric system. Distributed generation, or DG, refers to smaller power systems connected at the distribution level that can supply power to the grid when needed. There are 3 types of DGs in ERCOT. Unregistered DGs are mostly rooftop solar systems owned by residential customers. These systems are connected to the electric grid, but not all of them actually push power onto the grid. Settlement-only DGs are often supplemental generation resources located at businesses where they can provide backup power during outages. These resources are registered with ERCOT and compensated for the energy that they export to the grid, but they are dispatched by the resource owner. Distribution generation resources are typically standalone resources. Similar to SODGs, they are registered with ERCOT and compensated for their energy, but they are dispatched by ERCOT and can also be compensated for providing additional services such as reserve power. Demand response, or DR, refers to lowering electric load when grid conditions are tight. ERCOT's markets allow participation by industrial and commercial customers who agree to reduce their load when needed. Electric providers may also implement their own load reduction programs, and certain customers may voluntarily reduce their demand in response to higher energy prices. By using all of these techniques, ERCOT is able to operate a reliable electric grid for the people of Texas. To learn more about DG and DR, visit ERCOT.com. Transmission lines are high-voltage power lines that are used to move electricity from power plants to consumers. These lines are interconnected throughout Texas and make up the ERCOT electric system, along with power plants, substations, and other electrical equipment. The need for new or upgraded transmission lines is typically driven by load growth and a changing generation fleet. ERCOT oversees the transmission planning process, but transmission service providers, or TSPs, build, own, and maintain the transmission equipment. On average, most new transmission projects take 2 to 6 years to complete. Let's go over the steps in the transmission planning process. First, ERCOT and the TSP will identify a system need and determine the best solution. Next, stakeholders will review the TSP's proposed project through ERCOT's Regional Planning Group. ERCOT staff will perform an independent review for projects that cost over $100 million and/or require a new right-of-way, meaning that some portion of the new project would have to be built on private land. Projects that cost over $100 million are also reviewed by ERCOT's Board of Directors and need to be endorsed by the board before moving forward. If a transmission project requires new right-of-way, the TSP will communicate with landowners who may be impacted by the project. The TSP will then submit an application to the Public Utility Commission of Texas requesting permission to build the project. The PUC is responsible for approving the application and determining the final route for the project. Once the TSP receives approval from the PUC, it can finalize its improvement designs, order necessary materials, and begin construction. All transmission projects in ERCOT are paid for by consumers in the form of a monthly fee on their electric bills. For more information on the transmission planning process, visit ERCOT.com.
So anyway, this is the duck curve. So this is the graph, and this is the time, and this is the electricity demand from non-solar things. So coal, or gas, nuclear, whatever. The electricity that comes from those has to follow this curve, and when the sun comes up, depending on how much solar generating capacity there is, those other things need to shut down so that solar can take over. So these other generating systems have to decrease depending on how much penetration of solar there is. So this is for California. This was in 2012. There was almost no solar in 2012, so they just worked away like that without much of a change. A little bit of a peak in the late afternoon. Everybody gets home, cooks dinner. But then as solar started to penetrate, 2013, 2014, penetrated more and more. That is, more and more solar utility scale solar panels, or in California, residential as well. It became a real challenge to shut down electricity generation from the non-solar things and then ramp it back up in the afternoon when solar drops off. So it was this shape that was noticed in 2017 and probably 2018 that made people say, oh, that looks like a duck, right? There's the head of the duck, and there's the back of the duck, there's the tail of the duck, right? That's why we call it the duck curve. So if you don't understand that, then it's the best thing in the energy. I think it's the best thing in this class is, the duck curve. It's just funny. But the name is funny, but the problem is not. right? Because this is a serious problem that can only be ameliorated by increasing use of battery storage. So what would happen if we had a lot of the batteries to take this? We could take a lot of this energy and store it, for peak times in the afternoon. So, if you had a battery that could take solar electricity generated electricity, 1 or 2 in the afternoon and save it to be used at 9 or 10 at night, 8 or 9 at night, you could solve the problem. And this is what's driving this growth in battery storage on the net. It's the growth of utility solar and the fact that there's nowhere to put it unless there's more battery storage. So this is a really interesting evolution because battery storage was not an issue until solar and wind energy became big. And it's less of a problem for wind than solar, because solar is so predictable. Every day at 6 a.m, you'll start generating solar electricity. Every day at 6 p.m, you'll stop. Whereas wind is not quite like that. That's a little video.
When you flip a light switch, you expect it to work, right? All of your appliances work because your power company has electricity ready to transmit for a lot of customers. And utility companies have gotten really good at anticipating that demand.
If the grid managers are doing their job, you should never notice any of this.
But a rise in solar energy production is making their jobs a bit more complex. Here's a chart that explains why. It's showing demand for electricity at any given time of day. The power companies supply the least amount of power overnight. Then it ramps up in the morning. Everyone's woken up and business gets going. Then at sunset, energy demand peaks. Utility companies will update models like this to operate as efficiently as possible. But the introduction of renewable energy, particularly solar energy, has started causing problems in these demand curves. In 2010, solar panel deployment really started taking off. Most of those installations took place in California, so researchers there started looking into it. They found that the sun produces the most energy at midday, and when you factor in that new midday production, your demand curve changes like this. Every year means new solar capacity, which makes midday demand dip lower and lower. Researchers call this drop in demand the duck curve.
From the grid manager's perspective, the people whose job it is to constantly balance generation and demand, it looks like a drop in demand.
That drop in demand creates two problems. The first has to do with the intense ramps in the new chart. As the sun sets, solar energy production ends, just as the demand for energy typically peaks. Power plants then have to rapidly ramp up production to compensate for that, which is kind of hard to do with the current fleet of power infrastructure. The second problem is economic.
Say you have a couple of nuclear and coal plants. Those plants are only economic when they are running all the time, basically. They run around the clock. And if you have to turn them off at midday, it completely screws up their economics. And plus, lots of utilities just have contracts with those power plants to keep them running all the time. So that creates sort of an artificial floor. If solar generates too much power and there's no use for it, there's no one to consume it, then grid managers just have to turn some solar panels off.
If they didn't, we could risk overloading or even damaging the power grid. So we throw away some of that extra solar energy.
Effectively, what's happening is that solar power is being wasted.
That waste, curtailment, is the big challenge moving forward for solar energy.
If you want solar eventually to power everything or close to everything, you've got to figure out some way of shifting some of it to the nighttime, right? Because the sun's down during the nighttime. The more power can be stored, the more you can sort of let solar rip.
While the grid managers figure out how to serve this new supply and demand, this duck is the greatest challenge facing renewable energy.
All right. Now the book moves on to sort of the context for sustainable energy and talks about previous energy transitions. So here, this is out of your book, and we're looking at the years 1850 into the future a little bit, and then how we got our energy. Do we have a question there?
Yeah, I'm just curious, is the duck curve really a problem now that they've got all these solar trackers on the panels?
Yeah, the sun still goes down, right?
Oh, yeah, but at night, but I mean, it doesn't drop off as dramatically during the day.
Right. So
The output would be fairly consistent, I would think, during the day if you got solar trackers on it.
Oh no, because the sun's lower in the sky, so it we'll talk about that when we talk about solar energy, but it is not a step function. And we'll see that. You can see that on the ERCOT grid. It rises in the morning, peaks, midday, afternoon, and falls off, starts to fall off. But yeah, it's less of a gentle slope than it used to be because of solar trackers. All right, so we're talking about energy transitions. So energy transitions are shown here. So this is primary energy source for everything. So just so you know, electricity wasn't even a thing until around 1880. So the first energy sources was fuel wood, right? There was lots and lots of trees. People chopped them down, used it for heating, whatever else. And slowly, coal became more and more important. And coal became more important in terms of I think this is for the United States in around 1890, almost the beginning of the 20th century when that transition happened. At the same time, oil and gas started becoming important, right? That sort of oil was discovered in the United States in 1859, but it really didn't find its use until the automobile really started stoking things up. So this first energy transition to coal happened around 1895 or something like that, and that peaked, in 1910 as oil and gas became more and more important. And wood energy was still used, but it's basically tailed off to nothing now. And then as oil and gas came up, it surpassed energy production around 1950, and coal continued to drop, and it started rising again sort of during the oil crisis in the 1970s, because we have lots of coal and less oil and gas. And then so oil and gas has been rising. Now it's showing this falling off, but it's a percentage. So renewables are now on this part of a growth curve, and when obviously we would like to go this way, it might go this way. It's not going down. There's no way. We will see why that is, but we're in the midst of so this is one energy transition. This is the second energy transition. We're the renewables. That would be the third energy transition. Okay. So one of the interesting things is the evolution of how the United States became electrified. So this basically starts from 1882. This is a very interesting scale, right? This is in log scale megawatts, from 1 to 1,000,000 megawatts. And you can see this very rapid growth. The first electricity generating station in New York City in 1882. Then the development of Westinghouse's Niagara Power Plant, basically using Niagara Falls to generate electricity. And then the Public Utility Holding Company Act of 1935, which was important. and then the oil embargo, Clean Air Act, and where we are today. So, this growth of the electrical grid from nothing in 1880 to so important today is a remarkable part of the story. So this is all against the context of the desire to reduce CO2 emissions from the expected 23 gigatons a year to something like 10% of that. So these are the way that the International Energy Agency thinks we can do that. And so the percentage of the CO2 reduction mission, the largest part would be coming from increasing the efficiency of producing and using electricity. The second largest would be, from solar energy, then wind. Nuclear is a big part of this plan. Carbon capture and storage, which is something people talk about a lot, but is done very little of. Moving to biomass, and I've already had my comment about that. Hydropower, other renewables, and I guess fuel switching and power plant improvements. So it's a very ambitious scenario, but you can see that it requires a lot of different things. But most importantly is using electricity better. So there are many ways to generate electricity. So how do companies and investors make decisions about which kind to build or invest in? And they do something that's called a return on investment analysis. They don't just say, oh, we need to build more solar because we need to save the planet. No, they look at their portfolios and make reasonable calculations about what is the return on my investment. Now, there's two kinds that we'll talk about. One of them is the energy ROI, the energy that you put in versus the energy that you get out. And the other one, which is more important to investors, which is the financial ROI. If I put in this amount of money, how much money can I reasonably expect to get back? So let's talk about what the energy return on an investment is. So in energy economics, the energy return on investment, sometimes also called energy returned on energy invested, is the ratio of the amount of usable energy, sometimes called exergy, delivered from a particular energy source to the amount of exergy used to produce that energy source. A little confusing. But if you look here, these are the EROIs for different electricity generation technologies. So what it costs to build a coal plant and mine the coal, what it costs to build a natural gas plant, and in terms of energy, nuclear, hydroelectric, geothermal, wind, solar, photovoltaic. You can see here that the energy ROIs for different electricity generation technologies is maximized for hydroelectric, but finding sites where you could put in a dam and a hydropower plant there's fewer and fewer. We've got very few modern projects in the United States. China has lots of them. Then there is the cost. Your book goes into the cost of energy production. So the capital cost per kilowatt capacity is one way to compare the cost of an energy system. So the costs are the capital costs plus the maintenance and fuel costs. And the amount of energy produced for sale depends on plant capacity and the number of hours that the plant produces at capacity. And this brings us to Lazard, which is a company in Switzerland that does a very good job of doing these kinds of analyses. So Lazard it's got a very nice website, and it's all over the world. So And Lazard has opportunities for students. So if you're interested in exploring this, go to the Lazard website and see what student opportunities there are. So they every year they put out their assessment for the levelized cost of energy. This was last June's. You can download it if you want to get it in its gory detail. And the levelized cost of energy is a very important concept because it measures the lifetime costs divided by the energy production. So it involves calculating the present value of the total cost of building and operating a power plant over an assumed lifetime. So it allows you to compare different technologies, wind, solar, natural gas, with different lifespans, project size, different capital costs, risks, returns, and capacities. And this is very important for making informed decisions about what should happen next. So here's a simplified LOE concept. So here's your energy system, right? So you've got, it's going to be a pretty cheap project. It's $100 initial cost. So you put in this plant, it costs you $100. But that also includes the financing, right? You're not paying for this out of your pocket in most cases. You're going to take a loan. And then you've got annual expenses, right? You have to include that in. So you have an annual cost per year of $125. And this project will generate 1,000 kilowatt hours. So the levelized cost of energy in dollars per megawatt hours is, 12.5 cents per kilowatt hour. Okay, that's not a realistic depiction of the real LCOE, but it captures the main elements. So here's the way that Lazard looks at LCOEs for different kinds of power generation. So here's solar photovoltaic, community, utility, photovoltaic where there's linked utility and storage, geothermal, onshore wind, offshore wind and storage, offshore wind. And then there's conventional generation, gas peaking, U.S. nuclear, coal, and gas combined cycle. You remember we saw two kinds of gas on those pie charts, and that's what we're looking at. Gas peaking is very different than gas combined cycle. So there's ranges here. So this is dollars per megawatt hour. So you can see it's all over the place, but you can imagine that an investor thinking about what would be the best thing to make. Remember, you're selling electricity at the same price, regardless of how it's made, whether it's made by solar or burning coal or nuclear or whatever, you're getting the same price. So you can say, oh, well, that looks like I should think about gas combined cycle or maybe solar utility. But you can see here, where the emphasis is on now. And one reason why nuclear is so unpopular is it's so expensive. The levelized cost of energy is so expensive. But these things that are in dashes are more uncertain than things that are in solid. So it's a really interesting way of thinking about what projects to move towards. You might want one kind or another because it's your own predilection, but any investor is going to be paying attention to these kinds of numbers. So now there's a sensitivity to U.S. Federal tax subsidies. Some forms of energy are favored more than others. In the last administration, solar and wind was favored, and the tax subsidies benefited those. Present administration, they're much more interested in coal and nuclear. And I don't know what the status of the subsidies are But one can imagine that in the present environment, the levelized cost of energy with taking into account federal subsidies, tax subsidies, is changing. So that complicates things. All right. So one of the things that comes from looking at these levelized cost of energy analyses over the years is the cost of renewable energy has gotten much cheaper. So this one is onshore wind energy. It's pretty much gone down as low as it's going to go. It's coming up a little bit, but you can see it's not changing as much. Whereas solar has gone through this tremendous decrease from 2009 to 2025. And this is motivating more of these projects. But at the same time, we've got the storage problem that has to be dealt with, and that is motivating a lot of interest in battery storage.
A different kind of energy rush is sweeping across America's petroleum superstate.
Texas still holds vast oil reserves, but it also has a lot of sun, wind, heat, and demand for electricity.
It's not a new technology. In fact, it doesn't actually generate energy at all, but stores and releases it at just the right time.
Batteries are becoming a more critical and important part of our grid every day.
The batteries building up across the Lone Star State are soaking up huge amounts of electricity from another surge in renewable energy generation.
We have more wind than the next 4 states combined, and we just passed California in terms of utility scale solar.
Is not because of an aggressive state push towards decarbonization. It's because in Texas, it's relatively easy to build infrastructure and big projects than in other states.
Renewables have added vital capacity for the state's energy authority. Electrically separated from the rest of the USA, it can't rely on other states in a crisis. But the influx of solar energy in particular has meant that the regulator has had to juggle a fundamental switch in peak demand.
It actually has shifted to later in the evening when the sun starts to set, the solar energy has gone away, but it's still warm and hot outside, so the air conditioning load is still very high. Those solar ramp periods have become the highest risk periods on the grid during the summer.
And that's where batteries, or more specifically, battery energy storage systems, can step in, discharging what can be a grid-saving boost to electricity supplies.
Just a couple of days ago, there was an outage of a large generation coal plant, and there are enough batteries now that they jumped in, and batteries can deploy in microseconds. So they were able to stop any issue from happening. The grid stayed stable.
The output from this single 100-megawatt array could power at least 20,000 homes. Strategically positioned near the energy-sapping data centers in the metroplex of Dallas-Fort Worth, it's only a few years old, but already being superseded by the next generation of larger battery systems coming online.
We're going to take excess wind and solar generation mostly coming out of the Texas Panhandle, where there aren't as many people. That's going to be held in the battery, and then we're going to put it back out on the grid when the need arises.
While one unit was offline, it was safe to see inside a typical battery energy storage box.
Each one of the little silver boxes is about 22 small lithium-ion battery cells.
And how many homes could a system like this power when it's online?
A system like this could probably power about 22 homes. It's just for this one unit.
While California still has the most battery capacity deployed in the US, one projection has Texas overtaking it in 2026. If and when planned systems come online. A surplus of cheap renewable energy is just one factor behind such explosive growth.
So in Texas, it is going to be pretty much a pure economic play. So all of the batteries being deployed in the state are because they can make money.
The uniquely open, deregulated nature of the whole energy market in Texas means big profits can be made in just a few hours.
So it's mid-morning, the sun is up, and hundreds of solar energy projects across the state are rapidly ramping up their power production. That's having the impact of depressing electricity prices, which means we're naturally incentivized to charge from that energy right now. We're then going to hold on to it for the majority of the day. Sun goes down, people come home from work, turn on their air conditioners, and we're going to discharge that energy for a profit.
Of course, it's not always quite that simple.
Prices can be volatile, ranging from negative territory to thousands of dollars for the same unit of electricity.
The market is constantly comparing supply and demand and producing price signals for electricity products. We have a wholesale power market team that is watching the forecast for solar, it's watching the forecast for wind, and it's watching the forecast for load. And without a doubt, our net income is dependent on their skills as traders.
Those kinds of ups and downs are one of the unique characteristics of the energy-only market, but that volatility helps to incentivize the right type of generating resources coming onto the grid.
Juggling numbers in a constantly changing market is just one of the variables in the battery storage game. Systems are expensive to install and maintain, and many components have to be imported from China and other external sources, leaving operators vulnerable to supply chain interruptions.
I think that's something that all of us are weighing a bit. We also have some political wins as well with discussions about tariffs on Chinese batteries, and so you have to weigh that into your calculation. It's a constantly changing landscape.
Oversaturation is another potential risk factor, as more operators and batteries enter the easy-to-access Texas market.
Is there a risk that the bubble ultimately bursts?
The question is exactly how many batteries will come online, how quickly, and how quickly relative to some of the expected growth that we see in load and solar. We think there's enough room for a whole lot more batteries on the grid.
You know, batteries do eat their own lunch. So, you know, they reduce high prices and increase low prices. But with the demand growth projections we have in this state, it seems like there's a lot more room for more.
Texas has topped the tables in US population growth and become one of the leading data center markets in the world. Add to that the ongoing electrification of transport and industries, including oil and gas, and it's no surprise that the outlook for energy demand and the battery storage business it feeds seems bright.
Back in 2017, a couple of youngish billionaires got themselves into a bit of an exchange on social media about battery energy storage. One of the billionaires was the Australian entrepreneur Mike Cannon-Brookes, and the other one was, of course, Elon Musk. We all know the outcome, don't we? It was the 100 megawatt Tesla lithium-ion battery installation at the Hornsdale Power Reserve, shipped, installed and commissioned within 100 days. The Australian Prime Minister at the time derided it as a pointless gimmick. But it turns out that would have been a better description of himself than the big battery, because the installation is reckoned to have saved South Australia an estimated $100 million in grid balancing costs in its first 3 years of operation, and is now 50% bigger and routinely providing crucial inertia services to the state's grid system. In the year the Tesla battery was installed, the world's largest energy storage medium by far was pumped hydro, with about 150 gigawatts of capacity, a position that looked pretty much unassailable. Things have changed since then though, haven't they? While global pumped hydro capacity has grown to almost 200 gigawatts in 2024, utility-scale battery energy storage has rocketed up from almost zero to more than 150 gigawatts in the same timescale, and the trajectory of travel looks set to move the technology ahead of pumped hydro at some point in 2025. Nowhere is that rise being more keenly felt than in the United States of America. Largely as a result of the Inflation Reduction Act, we could be looking at more than 40 gigawatts of grid-scale battery energy storage in that country by the end of next year. So are we finally seeing a quiet revolution on America's tired old grid system? Hello, and welcome to Just Have a Think. If you live in a US state other than California, then you're probably a bit sick of hearing how the Golden State is leading the way on solar power. I get one of these sorts of charts in my face on social media just about every day now, showing me how Californian sunshine makes up the vast majority of daytime electricity generation. It's the famous duck curve that I've talked about a couple of times in recent videos. But even that chart's been changing rapidly over just the last 3 years or so. Hydro has continued to grow, but the biggest difference is this astonishing increase in battery energy storage from pretty much zero in 2021 to something like 10 gigawatts today, displacing almost half of the gas demand that used to sit there between 7 p.m. and 10 p.m. when most folks get back from work and start consuming energy at home. In fact, according to Bloomberg NEF, since 2020, California has apparently installed more utility-scale battery energy storage than anywhere else on the planet outside China. The good folks a bit further east in the Lone Star State would claim a similar level of advancement though, and with some justification. Texas is obviously best known around the world for its prodigious production of oil and gas, thanks to striking it lucky with the 75,000 square mile Permian Basin. But they're also by some margin the largest wind power generator in the Union, and they're quickly catching California up on solar PV as well. The Texas grid operator, ERCOT, has recognized the way that utility-scale battery energy storage can facilitate the implementation of intermittent renewables, so they too have ramped up the battery installs. According to the US Energy Information Administration, or EIA, Texas now has more than a couple of dozen installations of 10 megawatts or more, another half dozen or so topping 100 megawatts, and several pushing up towards 300 megawatts or more, something that would have been regarded as pure fantasy just a few years ago. And we all know the main reason why, don't we? It's the absolutely astonishing improvements in battery technology coupled with a precipitous drop in prices in recent years that look a bit like a boulder dropping off a cliff when they're plotted onto a chart. In the US, all of that has been really turbocharged by President Biden's Inflation Reduction Act, which now applies attractive tax credits to battery storage installations. And as more and more batteries have been deployed, grid operators have come to realise that they're not some kind of annoying bolt-on that they have to suffer in order to get renewables onto their systems and tick their decarbonisation target boxes. They're actually an extremely useful addition that can stabilise transmission frequency, reduce the reliance on expensive gas peaker plants during peak periods, and prevent brownouts and blackouts in emergency situations like heat waves and wildfires. Power companies have also realised that they can fill up their batteries during off-peak hours when generation is cheap or even price negative, and then sell those stored electrons back onto the grid at busier times of day when prices are higher. In California, for example, that means charging up in the middle of the day when there's often more solar power available than the state can use, and then discharging them during the peak evening hours. It's a system the industry bods call
talked about. So there's other costs of energy development, and one of the big ones is land. And I'm sure if anybody has any questions, don't hesitate to ask. We always love a conversation in this class. So, so here we're looking at, out of your book, a table that gives you the area in square meters per gigawatt hour. So you can see that, photovoltaics are going to require a big area. Concentrating solar, which is a kind of solar energy, which we will talk about. Similar large areas. Geothermal, much smaller. Wind, much smaller because they're not using all of the land. You couldn't graze cattle in a solar farm, but you could graze cattle in a wind farm. Natural gas plants, coal, and nuclear. So, land is an issue. Obviously, if you need a big area, you want someplace that land's cheap. And fortunately for Texas, that's West Texas. And nobody wants to live out there unless they have to. And with very few exceptions, those are known as crazy people. So that's a good place to put solar stuff and wind stuff. So then we
hand up from John
yes,
Myers.
Yes, John.
I'm just backing up that last slide there. Why is coal so much area less used when you got the mine and you got the plant?
No, it's not. Doesn't
natural
include
gas.
The mine. Doesn't
What?
include the mine. Doesn't include the mine.
Still,
It's, a,
a
it,
gas
it's only the plant.
coal
These are
plant's
just-
got to be bigger than a natural gas plant.
Well, apparently not. I can't answer your question in detail,
Okay.
but I mean, all of those are fairly small. Natural gas, coal, and nuclear compared to solar. Well, geothermal, natural gas, coal, nuclear, they're all relatively small footprint compared to solar. Right. So if somebody wanted to put a solar photovoltaic array in the city of Dallas, that they would run up against incredible land costs, right? And other competitions. Whereas, go out to West Texas where there's lots of empty land, do it out there. Eastern New Mexico, West Texas.
That's fine. I just wanted to see if I understood.
Yeah, it is interesting. And those numbers are approximate. All right, so let's talk about energy efficiency and conservation. So in 2019, the average annual electricity for a U.S. residential utility customer was 10,700 kilowatt hours. So that's an average of about 900 per month. Louisiana had the highest annual electricity consumption at 15,000 kilowatt hours per customer. Hawaii had the lowest at 6,000. You can see the benefits of being able to live where you can keep your doors open, your windows open. Residential buildings, about 40% of all energy, end-use energy in the U.S. and greenhouse, 74% of U.S. electrical power. That's surprising because previously we had said it was a much smaller fraction. Oh, of total energy, I think is what it is. Okay, so it's just residential. And then 50% of the energy used in residential buildings is for heating and cooling and 20% for heating water. And it's just, as we know in Texas, residential air conditioning is the main contributor to peak demand. When you want, some people like their place to be air conditioned to 75 degrees, others want it 65 degrees. So, if once you set that thermostat, you're kind of establishing what your energy use is going to be. Okay, so this was kind of an interesting thing your book did. Back of an envelope policy evaluations. So in 2008, Al Gore proposed that by 2018, all U.S. electrical power be carbon free. McCain proposed more nuclear power plants. 1979, Carter proposed conserving energy. So let's assume 20% conservation. How many new 8-megawatt wind turbines need to be installed, assuming 40% annual capacity to accomplish Gore's objectives? What is the total cost? Assume $1,100 a kilowatt and land costs. And then, to do McCain's suggestion, how many nuclear power plants, 1,000 megawatts? Remember, Comanche Peak has two power plants, each of them about 1,200 megawatts. And remember, these are going to be at higher capacity. So what would be the capital cost at $8,000 a kilowatt? So you'd need 75,800 wind turbines, which would cost about $66 billion and cover about 2% of U.S. land area. And of course, the problem is that the wind it's not so simple because the wind varies from place to place. We're going to talk about wind a lot, so just keep that in mind. And then if we wanted to do it by all nuclear, we would need 263 nuclear power plants, and that'd be 2.1 trillion, given the present cost of nuclear, which is changing. As of 2020, there were 57 commercially operating nuclear power plants with 95 reactors in 29 states. And then some of them had multiple ones. But of course, the problem is, where are we going to put the nuclear waste and the environmental concerns that people have, some of them quite valid based on Chernobyl, Fukushima, and 3 Mile Island, which we'll talk about more in this class. So we want to be clear on base load and peak load. So here we're looking at a daily mean demand for electricity. So what you can see is that at midnight, most everybody's in bed, but some people are laid up, stay up later. But by 2, 3, 4 o'clock, everybody's asleep. Electricity use is at a minimum. And then, when people wake up at 6 or 7, demand goes up and then levels off during the workday. And then it goes up at night. But see how it changes. So these are the peak times for all of these months. But, June, that's July. No, that's December. And I guess that's June. Now, this is for the United Kingdom, so they don't really care much about air conditioning. What they want is heating. So their peak demand is in the wintertime. Okay. So, there's no sunlight. So if you're going to get warm, you're going to have to do it with heating in the house. So you have to, the electrical companies have to deal with these curves so that, they always want to keep demand a little bit below supply. So that means that during these times, they have to shut down some power plants. And during these times, they have to bring on new ones in order to match this demand. Very important thing to keep in mind. And of course, we saw this for Texas, and you can see, we know when it's hot in Texas. It starts getting warm in June and gets really warm in July, and then it's blazing hot in August and September, and then late September, October, it cools off. Now, this was 2022. This was what caused the problem, in that spike, that happened. All right, so we're going to watch a 1-minute video. Okay, you guys, any questions about that? The difference between intermittent sources and, baseline providers that are basically can be counted on all the time. This is an important part of the conversation about the transition to renewable energy that we always have to keep in mind. So how could utilities use batteries to flatten the daily demand curve? So what we're seeing here is obviously the duck curve. And this is for California going from 2012 to 2020, as more and more renewables, especially solar and wind, came in. This was what the other sources, natural gas, all of them needed to deal with. They needed to go away so that solar and wind could provide. Now, this is mostly solar because the wind varies more than this. The sun is very predictable. But look at this ramp up. This is the stressor of the grid, is as the sun goes down in an energy system with a lot of solar photovoltaics, the other sources of electricity need to ramp up very, very rapidly. So this ramp here is 13,000 megawatts in 3 hours. So if we could take some of this energy here and store it in batteries to be discharged here, then we could make this duck curve less, even with more solar power. And we wouldn't need this ramp, wouldn't need to be as steep or as stressful. So does that make sense to everybody? We'll get more into this. So utility scale battery storage is growing fast. So they in 2024 they were planning to install 15 gigawatts of new utility scale battery storage. So that's a lot since there was only 16 gigawatts already there. So it's going up a lot. Now, battery storage, you have to manage the flow of energy out of the battery, right? So if you want to augment the electrical production on the grid, you've got to manage this, because these batteries only store so much electricity, and if you put it all at once, it's over in a flash. But if you manage it so that and they do manage it, then you can come up with a better plan. And this is part of what ERCOT's dealing with now in Texas. All right, so this is what we are seeing. It is growing fast. The hostility of the present administration to these kinds of renewable energy things, solar, wind, batteries, doesn't seem to be having a big effect on the investment community, because what you can see is going to happen with the ERCOT grid is the electricity rates are going to go up in order to build these new plants. And if the energy prices go up, then there's more money for investment. The value of the electricity that's coming out of these batteries is worth more. It's a very interesting economics. Yes, John.
Somewhere I read, is this true that lithium only stores electricity for 4 hours?
Well, that's a pretty good characterization of what's happening. So if you get 4 hours out of a battery storage, it's a question of what current you take out of it. If the current is basically what determines it. So if you manage the current, it could last longer. Just like, if you leave your car lights on overnight, your battery might be dead, but maybe if you dimmed them, they would still be. If you had dimmer lights, maybe that's not the best example. But you see what I mean? I mean, those of you that
you're talking about the amount of current, I guess. I was under the impression it wouldn't actually even hold it for longer than 4 hours, period. That's why the Chinese are using sodium.
Oh, no. Lithium, rechargeable lithium holds its charge. And we'll talk about, how long how long a battery can hold a charge. It really varies with the number of life cycles, charge discharge cycles that a battery has had, right? With time. We'll talk about this.
Okay.
All right. And then we're going to talk about energy efficiency and conservation. So this is a very important component of trying to get to, if not zero carbon, as low of carbon as we can. This table is sort of showing you the sort of the allocations for reducing CO2 so that the 2-degree rise scenario doesn't happen. So what you can see here is, there's percent of accumulated CO2 emission reduction. So solar 16% of the reductions, wind 15, nuclear 13, carbon capture and storage, taking it out of the atmosphere, etc. But you see the biggest way to accomplish that goal is with electricity savings, by increasing the efficiency and the conservation. And we'll talk about that in this course. So here's an interesting plot showing the reduction in yearly fuel consumption, right, on the vertical axis versus the relative energy conserving investments. So this is cheaper, this is more expensive, this is a huge reduction, this is a small reduction. So you look at this diagram and you go, oh, the cheapest thing to do is to caulk your windows, right? That physical gap causes the outside to come in and the inside to go out. And then next is weather stripping, efficient lighting, basement and ceiling insulation, double glazing for windows in new buildings, storm windows, additional insulation and retrofit, and then a solar domestic hot water system. So, this is a very interesting thing to think about. We wouldn't normally think about it, but the fact of the matter is the best way to reduce our energy consumption is to get better at more effective, more efficient at using it, not wasting it. All right, and then a bit about commercial buildings. Now, what's interesting about commercial buildings is that they are constructed and demolished faster than residential buildings. So 1% of commercial buildings are replaced each year, whereas with housing, there's more and more people all the time, so very few housing units are torn down. So professional energy auditing is not required for residential buildings. Perhaps it should be, but it is required for commercial buildings. And this brings us to the LEED. Let's talk about this.
20 years ago, buildings were constructed as a series of independent systems, each created separately but working towards the same goal of keeping the outdoors out. When LEED was introduced in 1998, it challenged the status quo with the concept that buildings actually function as living, breathing organisms. Similar to the human body, each system has a different role, but they all must work together so that the body can perform. One cannot operate properly without the other. In the case of buildings, not only are systems not separate, but by honoring these interconnections, the building can be built and operated in a more sustainable and efficient way. For example, by considering insulation materials and daylighting, building managers can use less energy on heating and cooling their buildings. By bringing architects, engineers, designers, material specialists, and others to the table during the design phase, decisions can be made that position the building for excellence in operational performance. LEED has gone from a set of aspirations to a marketplace standard, where the technologies of energy efficiency and sustainability have become commonplace practices. As these advances changed the marketplace changed LEED. V4 is the LEED of the future, where we challenge the still new marketplace to go further, to make the next great leap toward better, cleaner, healthier buildings where people live and work. LEED, or Leadership in Energy and Environmental Design, is a green building certification program that recognizes best-in-class building strategies and practices across the globe. LEED promotes better buildings, places that complement our environment and enhance our communities, places that give people better, brighter, healthier spaces to live, work, and play. To receive LEED certification, projects pursue credits that earn points. Prerequisites and credits differ for each rating system. Teams choose the rating system that best fits their project. After the team completes the review process, the project is awarded a certification level based on the number of points earned. So, if you're serious about saving money, conserving energy, making better building material choices, and driving innovation, then LEED is the best choice for you. Ready to learn more? Visit usgbc.org/LEED.
All right, so UTD, we have some LEED certified buildings. So we have one platinum LEED building, that is the Student Services building there. We have 4 gold certified buildings, Bioengineering and Science, the Alumni Center, Engineering and Computer Science West, and the Sciences building. And then we have 3 silver LEED certified, the School of Management Addition, the ATEC building, and Residence Hall West 2014. And it's interesting that the one that we went with the highest was the first one. I guess they said, okay, yeah, we're not going to do it because that's obviously more expensive. That's how I read this. And then they went back to, okay, we're not going to do very much. And they said, well, we can do a little bit more, right? Because this is like the first, these are the second, and this is the third. but it's an interesting evolution at UTD. All right, and now energy use in transportation. That's obviously another thing that we need to do because transportation accounts for 30% of U.S. energy use, 92% from petroleum. Cars and light trucks, 58%, and large trucks about 23%. And that this is in your chapter 15. And you can see here we've got annual EV sales projections over time. Here, this is the actual one. This was obviously done in 2023. And then this is one scenario that goes up, and then this is, this was a rather pessimistic one, but, right now, that was what it was doing. I don't know where it is today. I think it's flattened a bit. But that's a very interesting development we'll talk about. Energy management in industry and manufacturing, we'll be talking about that in chapter 4. And of course, we'll be talking about conventional energy, which are right now is fossil fuels and nuclear power. So, fossil fuels, that's the second energy transition, and we sort of are more comfortable with that. Nuclear power is one of the most interesting topics because it's one of these things that people get very excited about one way or the other. But basically, we're using nuclear fission to generate steam for turbines to spin the copper wire. This is a baseload provider. Once you have it, you can't turn it off. So you basically it's part of your baseload providers. So in 2023, there are 436 nuclear reactors in 30 countries, which provided 11% of global energy production, with 92 commercial reactors in the U.S. We've already talked about Comanche Peak. U.S. nuclear energy produces about 20% of our electricity. There's no greenhouse gases to speak of. We do have nuclear waste, and the real problem is they're expensive to build and they take a long time. And then renewable energy, you were going to talk about that. Obviously low greenhouse gas emissions. Don't need to say a whole lot more about that right now. And then here we're looking at some ranges of global technical potentials of renewable energy sources from different studies. So here's our global electricity demand in 2008. We're obviously going to be higher than that, but not by orders of magnitude. This is a logarithmic scale. And so these are the range of estimates for the potential of these things. Right? Geothermal energy has huge potential, but the question is, potential doesn't mean it's going to be implemented because the investors are going to make very careful decisions about whether this is likely to lead to the return on income on investment, financial in particular. Ocean energy, it's got quite a range. It's lower. Wind energy, higher. Now, geothermal energy for heating, that's got a lot of possibility. And this is the primary energy. If the energy that exists, if we could tap it. So this is the biomass energy. This is direct solar energy. The amount of energy from the sun is so much larger than our demands for energy that it's an extremely attractive source because of that tremendous potential. But of course, we're only tapping a fraction of it, but more all the time. So this was an interesting article I saw in Forbes a while back, and I haven't found an update to it. So if anybody finds an update to this, just how good of an investment is renewable energy? And this study from Forbes said that at that time, renewable energy investments are delivering massively better returns than fossil fuels in the U.S., the UK, and Europe. Renewable investments in Germany and France yielded astronomical returns. In the United Kingdom, similar large returns. U.S. Tremendous returns. Then Forbes at that time found that green energy stocks were also less volatile than fossil fuel stocks. Despite the impressive returns from renewables, such figures had not triggered anywhere near the level of investment required to decarbonize the economy and mitigate climate change. That's a statement. And the total global investment in energy was down 20%, almost $400 billion compared to the 2019 because of coronavirus. That was that time. So I'd like to update this. So the Wall Street Journal sort of chimed in along the same thing, that the investors are learning to love wind and solar power, pension funds, insurance companies, other institutional investors. Mostly, obviously the green theme is attractive for political reasons, but these companies are especially interested in the return promise of steady long-term income. This is a little bit about that. So here's the levelized cost of electricity. We've talked about that before using Lazard. And here you look at solar fixed. It was just so astronomically expensive at the beginning of this century, and now it's just getting cheaper, right? Now there's two kinds of wind here. There's offshore wind and there's onshore wind. Offshore wind is here, this pale green. It's pretty expensive, right, to put a wind platform offshore, but it's getting closer to onshore wind, which is cheaper. That's why Texas is doing so well. And here's coal, right? Coal's getting more expensive. It's still relatively cheap, but there's reasons that it's going away. Natural gas. Where is natural gas? It's in here somewhere. It's under. Oops. Go back. Yeah, it's down. It's down here. Right there. I think that's it. It's very attractive. And this is the renewable electricity capacity additions by region. So China is leading by far the renewable energy investments. Europe second, the United States, India, and then the rest of the world. But it's going up. So mining and renewable energy. This course is, it's my opinion that students, to get ready for the job market, need to know something about where we get our metals and minerals. That is something about mining, and they also need to know something about energy. And the two are really closely related because renewable energy uses a lot of minerals and metals, much more so than burning fossil fuels. And so this is an interesting point. The greener we try to be, the more mining we're going to need to do. So the World Bank made that clear. So, for example, the amount of wind and solar energy needed to meet the goals of the Paris Climate Agreement would double the demand for metals used in those technology. But that's nothing compared to the batteries that we need to store clean energy, which would require 1,000 times more metals than today. So all of those materials come at a price. Much of it comes from countries where labor and environmental standards are somewhere between weak and non-existent. Take, cobalt, for example. It's used in lithium-ion batteries, and 70% of the world's supply comes from Congo. And they've got Amnesty International reports that children as young as 7 work in those mines and, leave them with all kinds of problems. And then there's another problem on top of the ethical ones. The U.S. is dependent on other countries for nearly 90% of the minerals needed for our national security. And you're seeing the federal government take an active interest in certain kinds of minerals and mines. So it's a very interesting combination of the need for you guys to know something about not only energy, but also about minerals and metals. So your book, goes on to talk about the fact that relying on imports from a friendly country like Canada, obviously this lecture was written a few years ago, is basically harmless, but there's no country we're more dependent on for these metals than China. And that relationship is more strained. The reality is the United States has lots of mineral resources. It's just that nobody wants mining to happen. And so if you wanted to open a mine in most states, the amount of time that it would take to do that and get through all the regulations is astronomical. So one of the examples is this Kensington gold mine in Alaska. Gold isn't important for energy, but the price has gone up from, basically doubled in a year. So this mine was supposed to open in 1993, but it wasn't able to begin operations in 2010. And in the 17 years it took to navigate all those regulations, the cost of building the mine increased almost 50%. So it wasn't able to put in all the investment it needed, so it had to reduce its production. And anyway, one of the things that we need to do is find a way to expedite that process. And we're not going to talk about that here. So, but I did want to let you know that we've generated a course which is called GEOS 5318, Minerals and Metals for Sustainability. And like this course, we're recording it, aren't we, Clinton? And we put it on YouTube. Okay, so all the renewable energy sources, wind and photovoltaics, have shown the most rapid reduction in costs and market penetration. The two are linked. So, and that's good for investors. But here's our energy. We're looking at the production of crude oil and natural gas. It's come up recently, but it's expected to start different projections, have different decline curves at different times. Natural gas, these are the projections, and these are projections for renewable electricity generation. So this is something we made. It sort of shows, it's kind of a fun video about the wind in West Texas.
Hi, my name's Eric Walker. I'm a graduate student at the University of Texas at Dallas, and we're here at Monahans Sandhill State Park in West Texas, where we can see wind at work. Texas can be a very windy place. Its landscapes in the past have been shaped by wind, and its future in many ways belongs to wind. The portion of the south-central United States occupied by the states of Texas and Oklahoma spans a region with tremendous differences in rainfall and vegetation. From dense forest and 50 inches of annual rainfall in the east, to desert with 10 inches of rain in the west. The dry west is also the windiest part of these states. The dry and windy conditions of West Texas and Oklahoma are perfect for making sand dunes and dune fields. There are many dune fields in the western parts of the Great Plains. Monahans in West Texas is the southernmost of these dune fields. You can find the Monahan dune fields easily on Google Earth, where it is about 4 miles long and a couple of miles across. Sand is not the only thing that the wind of West Texas and Oklahoma is moving. It is also moving electricity-generating wind turbines. The world needs new sources of clean, renewable energy, and the rapid increase in wind-generated electricity is helping to meet this demand. The windy western plains of Texas and Oklahoma and other states is home to increasing numbers of wind farms. Texas is by far the leader in the United States electricity production by wind, with Iowa in second place and Oklahoma in third. Wind energy production is rising rapidly in both Texas and Oklahoma. In 2019, wind provides 16% of Texas electricity and almost 1/3 of Oklahoma electricity. This renewable source of energy is rapidly increasing in both states. In April, we visited Monahan Sand Hills State Park to capture some of it on film. Hey guys, I hope you enjoyed our short video on windy Texas. I wanted to take a moment to say thank you to the staff at Monahan's Sand Hills State Park for treating us so kindly and letting us spend an afternoon filming on site. Then I also wanted to give a thank you to AGU. Without your support, these kind of projects wouldn't be possible. So stick around for a few more minutes and you can see how we celebrated AGU's 100th birthday here at UTD.
Happy 100th birthday, AGU! Okay, wait a minute. Start. 1, 2, 3.
All right. So you can see this incredible rise in electricity generation from wind in the United States. That was updated 2024. It just keeps rising. It might be flattening out. We'll see in the next few years. One of the interesting things is how this technology is evolving. So here we're looking at the size of typical wind turbines of different years. And what you can see, and we'll talk about why you want to get your wind turbines up away from the ground. This is what's happening. When you also need it, because if you have these big blades, this is a 250 meter radius, plane, whereas the original ones was 37 meters. Now it's 250. So it's always interesting to look up what's the biggest wind tower in the world, So the biggest problem with wind energy is the wind doesn't always blow, or it actually can be too strong. And so you can't rely on wind energy production to match peak demand. So that leads to uncertainty on the grid, something like the duck curve, but not as predictable as sunrise and sunset. So this is one I found this year. So one of the things you're seeing here is the amount of energy they can produce when they're optimally, right? So a half of a megawatt, 20 megawatts, and then the new one in China is 340 meters tall. That's incredible. And it puts out 26 megawatts, at optimal. That's with a 310 meter diameter blade. Unbelievable. Okay, and then we're going to get into solar photovoltaics, or PV. This is the one method that can directly convert solar energy into electricity without a spinning turbine. There's many kinds. The crystalline silicon modules dominate. There's both utility and residential scales. And the percentage of solar energy that is converted to electricity generation on a given panel is increasing, but in 2016 was 22%. And as a result, the cost per watt for these installations is decreasing very rapidly, or it was. Right. And now we see this. Look at the similarity differences between solar energy in the U.S. versus wind energy. So wind energy started, I guess, took off around 2006, whereas solar energy didn't take off till, say, 2013. But this has got an even steeper rise than wind energy. Quite amazing. So right now we're producing the equivalent of about 8 Comanche peaks in solar energy for the U.S. Now there's another kind of solar that's interesting, which is called solar thermal, and these are these arrays of reflectors. These are not photovoltaics. These are reflecting the sun's energy onto a point here, and they're using it to heat up some fluid to drive a turbine. So these are interesting because they continue to generate electricity after the sun went down. Now, this is the concentrated solar productivity since 1994 in megawatts of power. It's much less than the solar photovoltaics. It's equivalent to about 3 Comanche peaks in the U.S., whereas that's 8 Comanche peaks. And actually, this is worldwide. So we're comparing apples and oranges. But the point is, there's a lot less of this going on. But it is an interesting technology, and we will talk about it. Each of these individuals are called heliostats. 10,000 of them there.
And
yes?
I would like to point out that they look way more badass.
Yeah, they look almost like something out of science fiction. And then one of the things that is maybe not as sexy, but is definitely cheaper, is using low temperature solar collectors to heat domestic water. So solar water heaters, solar home heat, solar pool heating, things like that. There's no electricity generated, but the book says that 375 gigawatts worth of warm water is produced globally, right? Because otherwise you'd have to use electricity to generate that. And we'll talk about ocean and geothermal energy, which includes, the wave energy, and to a lesser extent, to a greater extent, tidal energy. We'll talk about that. And then geothermal power plants, we'll talk a bit about that. And so here's ocean energy from tides and waves. So in this case, the tides drive propeller to spin a cylinder of copper wire and generate electricity. This one, wave energy, turning it into electricity, is more complicated. This is one way they do it, these chambers. We'll talk about those things. And geothermal energy, we need hot rocks near the surface. That occurs where the volcanoes are, and plate tectonics controls this. So this is the world's plate tectonic plates. If you're near a plate boundary, you've got a good chance to have geothermal energy. But these are the 10 top geothermal countries in the world. The United States is first, Indonesia second, the Philippines, Turkey, New Zealand, Kenya, Mexico, Italy, Iceland, Japan, and the others. So that's the global is about 7 Comanche Peak power plants. So could we drill into the continental crust to a region of sufficiently hot crust, inject water that would be heated sufficiently to generate steam? Right? Look how hot the Earth gets in the inside. This is degrees centigrade. Water boils at the surface at 100 degrees centigrade. So if we could get down to, several hundred degrees, and that's the temperature varies as a function of depth, then we could have a very powerful energy source. And there's some interesting developments in this field. Then there's a bit about biomass and biofuel. This is burning wood, dung for cooking and heating. This is mostly poor countries. Also includes ethanol production from corn, which incredibly now is 40 to 70% of U.S. corn production. But we'll see it's not really renewable energy because it requires lots of hydrocarbons for cultivation and harvesting. But you routinely see ethanol coming from this production as a 10% blend with gasoline at the pump. And hydroelectric, this is, the first ways that we made electricity was this way. And it's basically using a hydrostatic head to push a turbine to turn a generator and make power. So it's only a small amount of U.S. energy production, although a larger part of electricity production. But even at that, it's about a third of all U.S. renewable U.S. electricity. There's some interesting things you can do with this, because what you can do is, electricity goes down in the evening after 10 or 11 o'clock. You can take that abundant, cheap energy in the evening and pump the water back up in the dam, and then you can draw it down to generate electricity when demand is high. And we'll talk a little bit about hydrogen. Now, hydrogen is changing fast because when I started this course, it was an energy carrier. It was like electricity. It was not an energy source. It has the advantage of being portable like gasoline, but it's now being found in wells. And there's a very exciting possibility that there may be commercial quantities of hydrogen that we could tap. So this is making hydrogen from water is complicated. So, you can make it from fossil fuels. You can make it, you can use nuclear energy to break water or fossil fuels, right? Hydrocarbons can be turned into hydrogen. You can break water, but that uses electricity, that uses energy to make hydrogen, which then you can use for powering fuel cells, which we'll talk about what a fuel cell is later in this course. So this is kind of the way it works. You use electricity to split hydrogen off. That gives you hydrogen, which you can use in a fuel cell and makes electricity. So the present technology uses that much energy, and the electrolysis procedure's only 67% efficient, and the fuel cell's only 60% efficient. So you end up getting 1 kilowatt hour, right? So you're using quite a bit more than you're getting in return. Now, you know, the advanced technologies, like all technologies, are getting better. So you can see that this is not an energy source; it's an energy storage device, unless we can actually find it in the ground, and then it's a whole different ballgame.